A very good morning to all of you. Welcome back to the day 5 of National Workshop on Radiochemistry and Applications of Radioisotopes. All the participants, you have to settle down as early as possible so that we can start our session. Thank you. The first session of today is production of radioisotopes by Dr. Tapas Das Garu. So now I welcome our resource person for the first session today, Dr. Tapas Das Garu, to proceed for his presentation.
So, good morning. So, I am audible till the end. So, welcome to the last day of this national workshop, and the first presentation of today is production of radioisotopes. So, in last 4 days you have heard a lot about the radioisotopes. Even from yesterday onwards, I have seen all of us are telling about radioisotopes. Started with Dr. Sitaram, he told about many radioisotopes starting 32 phosphorus and many other things. I also told a whole lot of radioisotopes yesterday. Now the basic question comes, how we will get these radioisotopes? So if you remember yesterday's presentation, I told that majority of the radioisotopes are man-made. So it is artificially produced. There are some radioisotopes occurring naturally, as mentioned by Dr. Sitaram yesterday, but those are not very useful for our day-to-day life application. So even when we are sitting in this room, you are getting some radiation doses, because there are some radioisotope presence in the bricks also. But those natural radioactivity is not useful for application purposes. So we need to artificially produce these radioisotopes. So before I actually go about the production of radioisotopes, let us have a look about the historical perspectives. So you know, in 1896, French physicist Henri Becquerel discovered that certain substances produces penetrating radiation of unknown origin. All of you know this, and this was later named as radioactivity by Marie Curie. In 1898, Marie Curie and her husband Pierre Curie discovered the existence of the elements radium and polonium, because they are working with a material called pitch blende, from where they could separate these two radioactive isotopes. In 1902, the Curies successfully isolated radioactive radium, again from same material. So Marie Curie and Pierre Curie, they won the Nobel Prize in physics along with Henri Becquerel in the year 1903 for the discovery of the radioactivity. Then Marie Curie is the first woman who won the Nobel Prize in physics first, and again in 1911 she won another Nobel Prize in chemistry. But the actual use of the artificial radioactivity started when Irene Curie and again her husband Frederick Julio Curie, they discovered the artificial radioactivity in the year 1935. So, what they did is they bombarded 27 aluminum with an alpha beam or with alpha particles rather that time and obtained 30 phosphorus. And yesterday you have heard the concept of tracer, how this radioactive element can trace the pathway. It may be a chemical reaction, it may be some function in the human body as I explained yesterday. So, the concept of tracer was given by an Hungarian scientist known as George Charles de Hipse. In 1943, he won the Nobel Prize for this concept of tracer. So, many applications in industry, as you will hear from Dr. Atanu after me, and yesterday I have presented and even Dr. Sitaram has presented yesterday. These are basically based upon the principle of tracer, and this concept was first given by Professor Hipse. You know, the story was very interesting, some of you may be knowing. He was staying as a paying guest in a landlord facility, and he thought that the meat what the landlady is given to him is basically the old things, not a fresh one. So, that time just the artificial radioactivity was discovered, as you can see it's 1935, and he was working with that. He brought little amount of artificial radioactivity, and as far as I can remember it is a phosphorus isotope, and some isotope, I do not remember what isotope, he brought it and mixed it with the leftover. And next day when the food came, he took this to his laboratory and he detected that the radioactive sample is present. So, that indicates that the landlady was using the leftover thing in the next day's meal. So, that is how the tracer has discovered, which indicates you can trace the pathway. So, this yesterday I have shown that what is the concept of isotopes and radioisotopes, you are all familiar with that, and here you see that around 2500 radioisotopes are radioactive. So, those are man-made. So, how to make this? But before that, you know, this radioisotopes undergo different types of decays. I think that has been elaborately covered by my previous speakers. That may be alpha decay, beta decay, that is positron emission, electron capture, gamma emission, and for heavy elements it is spontaneous fission. So, how to produce the radioisotope? Yesterday I skipped these slides for today. So, you can see this is the plot of neutron versus proton, and this black line is the line of stability. So, what falls in this neutron to proton ratio are basically the stable radioisotopes. Now, if we want to produce a radioisotope, that means you have to destabilize these radioisotopes. So, how it can be done? So, either you can bring it here, that is this side, green side, or in the blue side. So, either you can increase the number of neutron or you can increase the number of proton, and thus you can destabilize those stable radioisotopes, because radioisotopes are basically unstable in nature and they undergo continuous radioactive decay to reach the stable state. So, it is very simple that you have to change the N by Z ratio to produce the radioisotope. Now, how we can disturb the N by Z ratio of the stable isotopes, so that we can get the radioisotopes. So, there are broadly two ways. One is the nuclear reactor. So, all you know that nuclear reactor is a source of neutron. What happens in the reactor is the controlled fission reaction, where a fissile material undergoes the fission, producing all a series of radioisotopes along with neutrons, 2 to 3 neutrons per fission. One is used to maintain that chain, and the extra neutrons are available in the reactor, which can be utilized for the production of radioisotopes. So, one source is that you put a stable material in the reactor, and as it is a source of neutron, there are a lot of neutrons available in the reactor. So, you get neutron rich radioisotopes, which usually decay by emission of beta particle or maybe beta particle along with the gamma radiation. If you put a fissile material in the reactor, another thing can happen. As I told, it may undergo fission and it can produce a series of radioisotopes from where you can separate whatever the radioisotope you needed. So, these two things can happen in the reactor. Otherwise, we can go to the cyclotrons. Cyclotron is the particle accelerators, where a high energy particle impinge on the target and you get the neutron deficient radioisotopes, and those usually decays either by electron capture or by the positron emission. So, this is the basic scheme of production of radioisotopes. Now, coming to the reactor production, we will come to the cyclotron production after this. So, if we put a stable material, stable isotope in the reactor, so what type of the material we will put, I will come later. So, it can undergo a series of things. What can happen is a radiative neutron capture, followed by the charged particle emission, multi-stage neutron capture followed by fission, and neutron capture followed by indirect reaction. All of this thing can happen along with Gillard-Charman process, depending upon the nature of your target. So, and all of this can be utilized for the production of radioisotopes, but basically they are all neutron rich radioisotope, predominantly decays by the emission of beta particle or by the beta gamma. So, let us now discuss this process one by one. So, the radiative neutron capture, that is the most common process, and almost you can produce all elements can be put in the reactor if they are stable, and you can get we can produce a lot of radioisotope by this method. And neutron, you know, it is electrically neutral. So, there is no electrostatic repulsion when it bombards the target. So, thermal neutron is sufficient, because in case of thermal neutron, the cross section is much higher. Cross section means the probability of the reaction between the neutron and your target material. And majority of cases you produce the beta emitting radioisotopes along with gamma radiation. But one of the drawback of this method, though it is almost universally applicable, is that you get the low specific activity radioisotopes. Now, I think you are aware about what is specific activity. Specific activity means activity per unit mass. So, if I say take, for simplicity, if I take say 100 atoms of an radioactive substance, and if only 5 of them are radioactive, and compared to another situation where say 80 are radioactive, so where the 5 is radioactive is a low specific activity. So, out of, because when you are putting a target in the reactor, not that all the cold will become hot, all of them will not become radioactive, majority will remain as cold. So, what happens, I will go to the next slide to make it more clear. Say we are producing 60 cobalt, that is used for the teletherapy, as I told in yesterday. So, what we do is that we put 59 cobalt in the reactor, it undergoes neutron bombardment and produces 60 cobalt, which is a gamma emitter. But it is not that all the 59 will go to 60 cobalt, majority of them will not, majority of them will remain as 59, and only few of them will become 60. But there is no way you can separate between this 59 cobalt and 60 cobalt. So, the specific activity, that is activity per unit mass, will be quite less, and this is in some cases is a problem, particularly when you go to the medical field. We need the radioisotopes with higher specific activity. So, though this method is very useful and you can produce a whole series of radioisotopes by radiative neutron capture, that is by the simple neutron bombardment, the issue is that your specific activity will be quite low. Coming to the two-stage process, that is radiative neutron capture followed by charged particle emission. Here first a stable target captures the neutron, produces a radioisotope, and that undergoes some decay forming your desired radioisotope. And as this is the two different things, two different chemicals, we can separate one from other so that we can have the radioactivity with high specific activity. As for example, say if you see here 32 phosphorus, about which Dr. Sitaram was telling yesterday, we produce it from 32 sulfur. What we do is that you allow it to undergo NP reaction, it produces 32 phosphorus. Now here the sulfur and phosphorus, they are two different elements. So you can always separate these two chemically. In previous case, this is the same isotope, element is same, it is 59 cobalt and 60 cobalt. There is no difference chemically between these two, so you cannot separate. But here it is a two different element, so 32 phosphorus and 32 sulfur. So you can easily separate by the chemical means, and so that whatever element of 32 sulfur is produced, whatever isotope of 32 sulfur is produced, all you can separate. So all 100% will become radioactive. So specific activity will be very high in this case. One of the example is 131 iodine. So you take, what you take is 130 tellurium and you allow it to undergo N gamma reaction. So it produces 131 tellurium and it has a short half life, I think Shahir 1.9 hour. 1.9 hour half life. So it decays to 131 iodine. Now what you can do is that you can separate the iodine from tellurium, which we do on weekly basis to produce 131 iodine, and it is a no carrier added radioisotope. So all the atoms are radioactive. So its specific activity is very high. The third process is multi-stage neutron capture. So once you are putting a target in the reactor, so it is not necessary that it stop after capturing one neutron. It produces one isotope, maybe stable, maybe unstable, and that can capture another radioisotope. So like that it can go on. So this is called multi-stage neutron capture, and one of the radioisotope which is produced by this method is 188 tungsten. So what is the target is 186 tungsten. It first undergo an N gamma reaction forming 187 tungsten, again it undergoes another N gamma reaction forming 188 tungsten. And why this is important? Because from her we get 188 rhenium, that is a very useful medical radioisotope because its properties are very close to technetium. So all our diagnostic things are based on 99M technetium radioisotope, as I told yesterday. So you can make the same complexes, you can use the same ligand to complex with 188 rhenium, so that you can have its therapeutic analog. So technetium is a diagnostic radioisotope and rhenium is a therapeutic radioisotope because it emits by the emission of beta particles. But one of the major drawback of this method is that the cross section, overall cross section becomes very less, because as I told that hardly few atoms depending upon its cross section will be converted to 187, and that will again there will be few of them will be converted to 188. So yield will be very low until and unless you have a very high flux reactor. Flux is basically the number of neutrons available per unit area per second. That way we tell how many neutrons the target will see in its per square centimeter area in unit time in a reactor. Or more the flux of the reactor, that is more the number of the neutron targets is, the more will be the activity produced. So this kind of the reaction is only possible if you have a very high flux reactor, which are very limited in the world. There are only 4 or 5 reactors which have this kind of, the flux required is something in the range of 10 raised to 15 neutron per centimeter square per second. So this type of the reactors are available in ORNL, that is Oak Ridge National Laboratory Reactor in United States of America, then SM reactor in Russia, maybe BR2 reactor in Belgium. Such few reactors are available where you can produce a meaningful quantity of 188 tungsten. Even in our reactor, I think Shahir and his group has produced 188 tungsten. We can produce but not in commercial quantities. It is sufficient for our research. Maybe few millicurie you can produce, but not in the curie level, because our flux is somewhere in the range of 10 raised to 14. Maximum fluxes of the Dhruva reactor where we produce the radioactivity is 1.8 into 10 raised to 14. But we need around 10 raised to 15 neutron flux reactors to produce this kind of the radioactivity. Now another thing can happen, as I told, if you put a fissile material in the reactor, it can undergo the nuclear fission and it produces several radionuclides together, as you can see here. So these are the mass number. So particularly in this region you can see from 80 to almost 100, and again this region we say 130 to maybe around 150, we produce lot of radioisotopes in quite good yield. But you have to separate a particular radioisotope, so you need to do that kind of chemistry to separate a particular radioisotope, and the issue is their quantity is very less, and major problem is coming from the radiation. There will be huge radiation dose. So this is called the fission, nuclear fission produced radioisotopes. The advantage is, again, here you can have the radioisotope with very high specific activity, but you will generate lot of radioactive waste, very high level radioactive waste with very long lived radioisotopes. So you have to handle those radioactive waste. You have to have the facility of handling those kind of radioactive waste, as well as you need to do those kind of chemistry with such a high radiation dose. But this is one of the method by which many useful radioisotopes can be obtained. This is something, another reaction, another way by which you can produce the radioisotope, called neutron capture followed by indirect reaction. So what happens is that first a target undergo neutron capture, forming another radioisotope which behaves as a bombarding particle for another stable target. So as I have shown here, say 6 lithium, it undergoes N alpha reaction forming tritium, and this tritium then behaves as a bombarding particle for 16 oxygen producing 18F. But this kind of the reaction is of only theoretical importance. We cannot produce any meaningful quantity of the radioisotope for commercial exploitation. This may be good for doing research, maybe paper publications, but not for practical purposes. Now the last thing what can happen when you put a target in the reactor is called Gillard-Charman process. So these are the two scientists who have first discovered it. So basically there are some targets, very specific targets are there. When you put them in the nuclear reactor, they undergo N gamma reactions, and their recoil energy is so high that it breaks some of the chemical bond, and from where you can get a particular radioisotope. And here again, though it is an N gamma reaction, still you can get the radioisotope with high specific activity. To make it more clear, say if you irradiate KBRO3 in the reactor, it undergoes N gamma reaction. 81 bromine is converted to 82 bromine. In normal case, if you take 81 bromine, you cannot separate 81 bromine from 82 bromine. But here what happens, whatever 82 bromine is produced, the bond breaks, it gets separated, and you can separate it from KBRO3. So you can again produce it with very high specific activity. But the issue is only few radioisotopes can be made by this process, and I think we made 51 chromium by this process by irradiating potassium chromate K2CrO4 in our reactor. So this is another method, but with a very limited utility, because only for certain radioisotopes can be produced by this method. But the advantage is this is an N gamma, very simple process, but still you can have the high specific activity radioisotope. Now coming to the charge particle bombardment. So that we do in the cyclotron to produce neutron deficient radioisotopes, as I told that they usually decay by electron capture or by the positron emission. So I think you are aware about the cyclotron. Yes, you know what is cyclotron? Yes. So, here you can accelerate the charge particle. So, you know the principle, so I will not explain. So, you accelerate the charge particle and it impinge on the target, which is usually a thin target kept in the cyclotron, and the radioisotope is produced due to this bombardment. This you have seen this. This is the design of the cyclotron. These are the two magnets, and radio frequency is altered so that the particles are accelerated and it comes out and impinge in the target with a very high velocity. Here is the target, it gets accelerated here, comes out from here and impinge in the target to produce different radioisotopes. Advantage is that here again your target and your isotope are different element. So, you can separate these two, and so you get it with high specific activity. So, you can see here some of the medical cyclotron. These are the history, a very, very big and bulky facility. And now you can see the modern cyclotrons. It is a very small. These are the modern cyclotrons. These are for the target system, extremely complicated though. And these are the chemistry module. You have to do everything inside to produce the radiopharmaceutical. Like every day we do 18F FDG, yesterday I told, fluorodeoxyglucose for the detection of cancer. So, these are the module which is utilized, and these are the some modern cyclotrons, and we have in India at this moment around 24 medical cyclotrons available, out of which I think roughly 10 will be in the government sector and 14 will be in the private sector. So, these you can see the different reactions as I told, say 18F, this is the most common. So, you take 18O enriched water where oxygen is enriched with 18O, it undergoes PN reaction bombarded with proton, forms 18F. It has a half life of around 110 minutes, and here you can see it is fluorine, your product, your target is oxygen, that is basically water. So, you can separate fluorine from oxygen. As a chemist, it is not very difficult job. So, you get the radioisotope with high specific activity. So, this radioisotope production is the major strength of one of the major strength I will say of Department of Atomic Energy. Here you can see the Dhruva reactor, which is there in our institute, dedicated to the nation in the year 1985, and it is still working, and this is the major source of all the radioisotopes whichever is used in India for medical, for industrial, for agriculture, whatever may be the purpose. If it is not imported, it has come from this reactor. This is our new reactor, Apsara upgraded reactor in 2018. This is a pool type reactor, and these are the core of the nuclear reactor. Here there are the rods, fuel rods, and in one of the there are some fuel, in place of one of the fuel rod, these targets are placed for neutron bombardment, and these are the cyclotron. You can see here the first medical cyclotron of the country, again which was established by Department of Atomic Energy in our Radiation Medicine Center of Bhabha Atomic Research Center 200 in 2002, and it is still working, and we regularly produce different PET isotopes, or rather PET radiopharmaceuticals using this cyclotron, and this is the biggest cyclotron of the country, 30 MeV cyclotron, which has been established again by DAE at Kolkata, and which is working from 2018 onwards. Now, so far I have discussed about the different ways by which you can produce the radioisotopes. Now, what can be chosen as the target? So, not that anything and everything can be put in the reactor. Certain conditions you have to fulfill before those can be put in the reactor for irradiation. So, target should be as pure as possible. Why? If there is impurity, you will end up with other radioisotopes. So, your radionuclidic purity will be less, and those, if the target, if your radioisotope is not radionuclidically pure, it cannot be used in many places, particularly in the medical field. This is not at all acceptable. It has to be very, very low. We have a very stringent criteria of radionuclidic purity for medical applications. Then target should not be explosive, pyrophoric and volatile. This is self-explanatory. No gaseous product should be evolved during irradiation. And in majority of cases, we either use as a metal itself or by the oxide. Now, why oxide? Because it is, say we are producing lutetium. So, we use lutetium oxide target, because if there is something else that will also undergo the neutron bombardment. But what happens when oxygen undergoes neutron bombardment? So, it produces 17O. If the second neutron bombardment, it produces 18O. If there is consecutive third neutron capture, it produces 19O. Now, 17O and 18O are the stable. So, there is no problem, these are the stable thing, you are not producing any new radioisotope, and 19O is very short lived, it has a half life of 27.1 second. So, if we wait 10 half lives, nothing will be there from the oxygen side, that is 270 seconds only. So, within few minutes, whatever the radioactivity was produced due to oxygen will be decayed. That is the reason oxygen oxide from is preferred. As I told, metallic from you can irradiate, like tungsten can be irradiated as tungsten metal or as tungsten oxide. Carbonate and nitrates can also be irradiated, and nowadays we irradiate lutetium nitrate for production of 177 lutetium. Now, how we will put this in the reactor? So, if it is for a very short duration, even the plastic container can be utilized, but the irradiation has to be for the very short duration and also the lower flux. But if you use the moderate flux position and comparatively longer duration, or for the higher flux position, usually we use the very high purity aluminum can. Now, the question is why aluminum? The reason is it has a very high melting point, because when you will bombard, when it will undergo the neutron bombardment in the reactor, its temperature will be higher. So, it should not melt. The container should be able to withstand that temperature, and this will also undergo neutron irradiation. Anything you put in the reactor core, that will capture the neutron. But 27 aluminum, it produces 28 aluminum by N gamma reaction. Again, it has a half life of 2.3 minutes. So, again if you wait for some time, something like half an hour or 1 hour, whatever the radioactivity produced due to aluminum, 28 aluminum will be decayed. So, we will not have the problem from those radioactivity, or you can use the quartz, because on that case it produces 30 silicon goes to 31 silicon. It has a half life of 2.6 hour. So, maybe we will wait 1 day after the end of bombardment. So, once the bombardment is over, we will take the product out of the reactor, store it for 24 hours, and then we will bring it to our laboratory. So, these are the typical aluminum can what we use. In the powder form, usually it is poured inside and it is sealed and then sent to the reactor for the irradiation. Now, what happens after irradiation is that it comes back to our laboratory and you need to radiochemically process it, which is again an extremely challenging task. Why you need to process it? Because you have to use it for industry, you have to use it for agriculture, you have to use it for medical purpose. So, you cannot use it as a powder, you have to make it a suitable radiochemical form. So, sometime it is chloride, sometime it is maybe like for technetium it is sent as pertechnetate. So, it has a particular chemical form, you have to convert this thing, and it is extremely challenging because you have a huge amount of radioactivity you have to handle, and the quantity of the radioisotope weight wise it is extremely small. It may be in the milligram level, sometime even in microgram level. Even in few microgram we can get a huge amount of the radioactivity. So, these are the lead shielded plants which are available in our facility, and you can see here the people are doing the radiochemical processing. It is completely remote handling, nobody goes inside. These are the lead viewing windows you can see here. Here these are called master slave manipulators and these are called tongs. So, you can see inside what is happening and you have to control everything from outside. because it gives a huge radiation dose. So, inside that whatever chemistry you do in the tabletop in normal inorganic chemistry laboratory, similar type of chemistry we do inside the heavily lead shielded plant to make it in the suitable radiochemical form before we supply it to the different hospitals or before we use it for the preparation of radiopharmaceuticals. Now, what are the difficulties in this radiochemical processing? As I told, radiation hazard, generation of radioactive waste which you cannot throw in the environment. You have to have the facility for storage, at least for the long term radioisotopes, long half-life radioisotopes. For short half-life, you can keep it in your laboratory to completely decay before you can discharge. Time factor, this is a very important point because for medical radioisotope all are short-lived. So, you have to finish it do the radiochemical processing as soon as it comes to your laboratory and send it to further for the production of radiopharmaceuticals. So, time factor is extremely important. So, we have to do it very fast. So, we have to be on our toes as soon as it comes from the reactor. We have to do the radiochemical processing and send it for the next processing. And as I mentioned, the quantity is very small. Only in majority of cases it is only milligram. Even in some cases it is microgram level, but that is good enough to produce a huge quantity of the radioactivity. Now, another concept I think already you know, radionuclide generator system. So, this is an extremely important concept, particularly useful for the short-lived radioisotopes for the medical purpose. So, in hospital, so maximum used radioactivity is 99 and technetium, as I told, it has a 6-hour half-life. So, we cannot produce in Dhruva reactor of Bhabha Atomic Research Center and send to all over India. What we do is that we produce molybdenum 99 MO because that has a 67-hour half-life and load it in the generator. So, what happens in the generator is that the long-lived radioisotope is put here. Here as you can see, it is a column chromatography generator. There are different types of generators. So, you put it here and what will happen? Your daughter product will continuously grow. This is after some time, say if you elute this with a solvent, what will happen? The solvent will pass through it. It is a evacuated vial. So, it will suck the liquid and whatever the daughter is produced, that will be collected here and parent will remain here. So, whatever the 99 M technetium will be produced, that will be sucked by this vial because we put saline here. So, 99 M technetium in the form of 99 M particulated will come here and will be accumulated here and 99 molybdenum will remain there. Again it will start decaying. So, every day you can come in the hospital in the morning and elute the 99 M technetium because this will follow the half-life of molybdenum. As you can see, this is the parent activity which is slowly decaying and this is the daughter activity 99 M technetium which is growing, and after some time you are eluting it. So, it becomes daughter activity becomes 0. Again it starts growing and so like this you can repeat the cycle depending upon the half-life of the parent. So, this is called, it is something like milking. So, it is called milking of the, just like milking of the cow, it is milking of the generator. So, you can get a short-lived radioisotope repeatedly in your laboratory or in your hospital for use. We just sent the parent isotope in the form of a generator. There are many, so these already I have explained. So, there are some of the generators and you can see photographs of some of the generators here. So, there are different types of generators supplied by different companies. So, this is PERS, that is supplied by Iran, ITG, Germany, these are IANCAS. So, there are many companies which supplies the generator, including our Board of Radiation and Isotope Technology, Department of Atomic Energy. So, now how will calculate what is the radioactivity produced? I think this already been taught to you. It is by this formula n sigma phi 1 minus e raised to the power lambda t, and this gives you how much activity will be produced in dps, disintegration per second. Here n is the number of target material, sigma is the cross section of the reaction that is known, that is the probability of a particular reaction to occur. phi is the neutron flux. So, again this is basically fixed for a particular reactor and for a particular position of that reactor, that is how much neutron it is seeing in per unit area in unit time. Lambda is the decay constant of the radionuclide which is produced, and T is the time of irradiation. So, if we know all these things, so we can calculate theoretically how much activity will be produced if I put a target in the reactor for a certain period, provided if I know the flux of that position, how much neutron this target will see in a particular time. So, but many times we see there is a discrepancy between what we calculate and what we actually measure after production. There are several reasons, because there are burn up of the target. So, after a certain time, so we are calculating n number of atoms, but that is not fixed. More and more atom with the time it will become radioactive. So, number of atoms are cold atoms are gradually decreasing with the time, but we do not consider this thing in the calculation, otherwise it will be very complicated. There are formulas, but usually not required, because very minuscule amount of the cold atom becomes hot. Another problem is the variation of the flux. It is not fixed. It depends on the power of the reactor and it often varies. So, we are calculating considering it has a particular flux, but it is not the case. It is varying with the power of the reactor, and sometimes your daughter product get lost because it can further capture neutron and it can go multi-stage neutron capture. So, many times these two does not match with each other. Now, as I told that how we will get the high specific activity from the reactor. So, if we look in this equation, see this n, this is the number of atoms, this is sigma, you cannot change, phi it is fixed for the reactor particular position. So, only thing we can do is that if we want to get the high specific activity, you can change the T or you can put in a higher flux position. So, if we irradiate, you can calculate very easily from this formula. If we calculate is for the 1 half life, you get 50% of the maximum specific maximum activity, 2 half life 75%, 3 half life 87.5%. So, usually we will irradiate 3 to 4 half lives of the radionuclide which is being produced. So, if it is a molecule having a half life of 1 day, so we will try to stop it after 3 to 4 days, so that we get around 90% of the maximum radioactivity, because after that it becomes a plateau. So, there will not much increase in the radioactivity, but at the same time there will be decrease of the radioactivity due to continuous radioactive decay. Now, I will just briefly mention about production of some of the important radionuclides. I will not go to much details, like one of the most important radionuclide is 99MO, 99 molybdenum, because from this we get 99M technetium, which is the bread and butter of all nuclear medicine departments. So, you have the two routes, one is nuclear fission, as I have already explained. You take uranium 235 or 239 plutonium fissile materials, they undergo the nuclear fission, produce 99MO, or you can take 98MO and allow it to undergo N-gamma reaction to produce 99MO, which undergoes beta decay to produce 99M technetium, which is very short after in the nuclear medicine centers. So, this is the nuclear fission, extremely complicated process, because you produce, as I told, lot of radioactivities with different isotopes, and you have to have separate from here the 99MO with a very high radionuclidic purity. But you see the specific activity, it is almost 1000 to 10,000 curie per gram. So, 1 gram of moly will give you 1000 to 10,000 curie of the 99MO activity. And you can see some of the photographs of our fission moly plant, which has started working for last 2 weeks. We are producing this fission moly. You can see extremely complicated and fully shielded facility. Another one, as I told, the simple N-gamma process. You take 98 molybdenum, allow it to undergo N-gamma reaction, which we do in our division regularly to produce 99 moly. But let's see the specific activity. It is just 1 to 10 curie compared to 10 raised to 3 to 10 raised to 4 curie what we get from the fission moly. It is much lower specific activity. So, I will skip this. So, this is the generator production facility which we have in board of radiation and isotope technology at our institute. You can see the generators are being produced. This will be supplied to the hospitals. So, molybdenum is loaded inside and you have to just take out the technetium in the hospital for production of different radiopharmaceuticals. This is another generator production facility. I am not going to the details. There are different types of generators and usually we supply two different kinds, cold tech and gel tech. So, the first one is the, what I show here is the, sorry, this is the cold tech generator facility. This is another type called gel tech. Now, coming to another isotope is 131 iodine. It is a beta emitter with maximum beta energies around 800 keV along with a gamma of 364 keV. As I told, it is extensively used in the treatment of thyroid disorders. So, we produce it from the tellurium, as already I have explained. 130 tellurium undergoes N gamma reaction forming 131 tellurium, which undergoes beta decay to produce 131 iodine, and so this is how we separate this. So, tellurium dioxide powder is irradiated in the reactor, and that is, after the irradiation is over, that is brought back to our laboratory, heated at 740 degrees Celsius temperature. So, whatever the iodine is produced, that comes out and taken away with the argon gas flow, and it is distilled. The distilled iodine is trapped in sodium thiosulfate and sodium hydroxide to make the alkaline solution of sodium iodide, where iodine is radioactive, and it is supplied to the nuclear medicine centers all over India for the treatment of the thyroid disorders. This is another generator, rhenium generator. As I mentioned, that tungsten need to be prepared for this generator. The parent is tungsten 188, and only the high flux reactor of the world can produce this kind of the generator. We can do it in our laboratory scale, but not for the commercial supply, because our reactor is not of that high flux. So, another isotope is yttrium, yttrium 90, that is another very useful isotope, again obtained from a generator. This is a very high energy beta emitter, 2.28 eV, but it has no gamma, it is a pure beta emitter. So, you can see here the strontium yttrium generator. The principle has been developed in our center, in our division. It is known as Kamadhenu in the, as per the Indian mythological creature, because it is a continuous source of 90 yttrium, because the strontium has a half-life of 28.3 years. So, once you load it, it can continuously give you 90 yttrium, and this is an electrochemical method. There are different methods of separation. So, from here you can continuously get 90 yttrium. You can elude the generator and get a weekly basis the 90 yttrium for different types of uses. Now, another extremely useful isotope is lutetium 177, whose use has been picked up in the last maybe 20 years, and nowadays we supply a huge quantity of lutetium 177 to our hospitals. So, it is a beta emitter, medium energy beta emitter. Maximum beta energy is around 497 keV, half life is around 7 days. It has the gamma also. So, you can produce it in two different ways. You take simply 176 lutetium. Of course, you need to take the enriched target to get it in higher specific activity. It undergoes the N gamma reaction, and you see the cross section is very high, 2100 Bern. It produces lutetium 177, our desert radionuclide. But one of the drawback of this method is that you produce little bit of lutetium 177M, which is a very long lived isotope of 160.5 day half life. So, it is a radionuclidic impurity in this. This is inevitable in this method, but the quantity is very less compared to this isotope. So, this is the method with which we prefer to produce it in our center. But there is another route. You take ytterbium 176, again highly enriched target you need. You allow it to undergo N gamma reaction, cross section is where minimum 2.85 Bern, produces ytterbium 177, which undergoes beta decay to produce again the lutetium. The advantage is it is high specific activity, because see, your target is ytterbium 176 and you are getting lutetium 177. So, you can separate lutetium from the ytterbium. So, you get in this process high specific activity lutetium. So, as I told that all 100 atoms will be radioactive, but in this case it is not. It is a comparatively moderate specific activity lutetium. but its specific activity is good enough to produce the radiopharmaceutical, because this is comparatively much cheaper compared to when it is produced to this route. So finally, I will just tell or complete my presentation by telling you about little bit of targeted alpha therapy, because this is now in the last few years it has become all over the world, it is becoming more and more popular, that how alpha is being used for the treatment of the patient. So you can see here some of the alpha radionuclides, alpha emitting radionuclides, which are proposed for the use of the radiopharmaceutical, making radiopharmaceutical, and this is already this 225 actinium and 223 radium. This is the first radionuclide whose alpha emitting radionuclide whose use has been approved for the human patients in the 2013 by US FDA for bone pain palliation application. Simply radium chloride is injected in the patient, 223 RaCl2, but presently which is majorly used is 225 actinium in the form of 225 actinium dotatate. As I told yesterday about lutetium dotatate, similar way actinium dotatate is used for the treatment of neuroendocrine cancers, and actinium PSMA 617 used for the treatment of prostate cancers. But here you look, it undergoes a series of alpha decay, it is not a single alpha decay. So 225 actinium undergoes 4 alpha decay, forming 221 francium, 217 astatine, 213 bismuth, and finally it goes to the stable 209 lead along with 2 beta particles. So it is a series of alpha decay. So in a short span of time, it gives almost 28 MeV of energy, where in beta we are getting around 2 MeV, it is giving 28 MeV of energy. So when the treatment with the beta particle fails, sometimes the doctors prefer to treat those patients with the alpha particle. So how to produce it? It is extremely costly at this moment, because it is not available in majority of the countries. So it has a many production route, but all are very difficult. So I will not go to the details of all the production route, but the 2 major routes are, one you can get it from 229 thorium. From where we will get 229 thorium? You have to get it from 233 uranium. That is basically a legacy waste. So unfortunately we do not have a lot of stock of the legacy waste. US have certain stock of legacy waste, from where they separate 225 actinium, and also it is available in the Karlsruhe, Germany. So from there they are separating this 225 actinium, but the total global annual production volume is approximately now only 55 to 65 GBq. That much only can be produced from this legacy waste, whatever is available at this moment, and that is not good enough to meet the world's demand. So that's the reason it is very, very costly at this moment. Another thing you can do is that you can use the cyclotron, and you can take P2N reaction using 226 radium as the target. But the problem again is 226 radium is not a stable isotope. It is again a radioactive thing. To put something in the cyclotron which is radioactive, it is extremely difficult, and it is compounded because it emits the radon gas, radioactive radon gas, which is again very dangerous. So you have to handle those things, and at this moment in India we do not have any facility for the production of commercial scale 225 actinium. Whatever the little bit is used in India are all imported, and the scenario is more or less same in all over the world, only there are very limited sources. So the cost of 225 actinium is quite high at this moment. Another important thing, I will just bring it to your notice, that say we are using doing lot of treatment with 177 lutetium. What happens? It undergoes beta decay, forming 177 hafnium, that is a stable isotope. Similarly, 131 iodine, it undergoes beta decay, forming 131 xenon. Or 90 tritium, it undergoes beta decay, forming 90 zirconium. They are all stable, but you carefully look here what happens when actinium is undergoing decay. When you are producing radiopharmaceutical and putting in patient's body, it will undergo a series of decay, and all are radioactive. So we need to do lot of studies to know what is the effect in the patient in the long term basis. Short term, yes, it is controlling the very difficult diseases, but we do not know what is happening in the long term. That only future will be able to tell when we will have sufficient number of patient data with the who have been injected actinium based radiopharmaceuticals. So, I think with that I will complete my presentation. So, thank you very much for your kind attention.
Any queries? Yes.
Hello sir, good morning. How the irradiation dose is fixed?
Irradiation?
Dose rate?
No sir, dose rate is not fixed. We calculate how much activity we require.
Okay.
And we use the A equal to n sigma phi. So, we know our flux position in the reactor, how much flux it will see. We can fix the irradiation time, whether we will irradiate for 1 week or 2 weeks or 3 days or 5 days, that we can fix. And we can only calculate, say this much activity we need to produce, and accordingly we will put the target in the reactor. We do not see the dose basically. Dose is checked. Once it comes out from the reactor, there are health physics team, they check how much dose is outside, and depending upon the lead shielding is given, so that it can be transported safely. Dose rate value for
Irradiation purpose?
No, there
How
is
many
no,
grade?
there is no dose rate value. We just put the stable target, put it in the aluminum can, send it to the reactor, and once the irradiated target comes, it is measured, and if it is in the safe limit, we put it of course in the lead cast and it is transported. So, there is no that way specific dose rate value.
Good morning, sir.
Good morning.
In targeted alpha therapy, we emit alpha particles.
Yes, please. Yeah, please, बोलिए.
But the alpha particles have very low penetrating
You are telling that how you use the alpha particle because it has a very low penetration power. Yes, you are right that alpha has a very low penetration power, but the issue is, see, it is a targeted therapy. It's not that alpha is somewhere and your tumor is somewhere else. With the targeting moiety like say PSMA or dotatate, we put it exactly in the tumor, so that it is already located in the tumors or tumorous cells, and then it irradiates the tumors. Yes, it can stop. Yes, but what is the cell diameter? It is much lesser than your paper thickness. So, it is only few, maybe even less than a millimeter. So, it will irradiate, but of course, you need to target it properly. If it goes somewhere else, it will irradiate the other cells. What is the production of?
17 oxygen.
17 oxygen. Okay.
There is also further production of 19O.
Yes.
Has very low half time.
Yes.
This radiation will affect the further production of the radioisotope.
No, because see, once you put 16O, so as oxide from oxygen is there, 16O will go to 17O, 17O go to 18O, 18O will go to 19O. So 19O is stable, and you are telling from 19O to 20O, you are asking like that? Yeah. 19O is stable. Oh, sorry, it has, yeah, you are right, you are a very, yes, very short half life, yes. No, it will decay fast. It emits some of the radiation. Yes, but it will be, see, what happens is that when we take it in the oxide form, a huge quantity of that isotope will be produced, a lutetium, huge quantity will be produced along with little bit of oxygen radioactivity. But once you keep it for some time, it has a very short half life, all oxygen will be decayed. We are not injecting it into patient, it is kept for some time. So, all oxygen will be decayed and only the lutetium activity will remain. Is it not clear? Okay, we can discuss in tea time, because I am also not able to hear you properly.
Any further questions?
So,
Yeah.
if there is no other question, I will just tell one more thing. So, I think people are interested in seeing this photograph. So, this I have taken from the product brochure of lutetium dotatate, which is used for the treatment of neuroendocrine cancer. Yesterday I told this is sold in the market in the name of Lutathera, lutetium therapeutic, from where the name originated, and this is their product brochure. So, you can see here it shows it is targeted. This is, I think, an owl most probably, and you see its eyes are the symbols of the radioactivity that indicates, just like owl, na, in the night they will target a particular thing. So, most probably they wanted that. So, I have just copied it from the product brochure of Lutathera.
Now I welcome Srimati B. Durgalakshmi Garu for the feedback.
Thank you, sir. Thank you for giving this opportunity. It's my pleasure to give feedback on sir's talk, and lot of thanks. As like yesterday, sir, today also sir has started his talk with a nice smile, with a systematic step-by-step explanation and presentation. Sir held our attention throughout the session. Yesterday talk, sir has actually brought to us to a doctor's cabin, I think, by showing NMI images, nuclear medicine images. And today, I think he brought us to a cabin of production activity centers of DIE institutes by showing original pictures of those activities, like what is that? Like first medical cyclotron, etc. So today topic in the today's session he covered various methods of production and selection of irradiation targets and how to select the containers also, and radionuclide generator systems. After production, how to calculate activity and how to increase, otherwise how to get high specific activity per unit mass. And sir also covered various isotopes, production and targeted alpha therapy. With the last slide also, sir hold our attention on those bird eyes, right? So with this, on behalf of all our participants, I express my heartfelt thanks to sir. Thank you very much.
Now we will have a short tea break, and
so this session we will be discussing applications of radiation and radioisotopes in industries, different industries. So in the first lecture, our Tapas Das sir has explained very well how radioisotopes are produced. Some of them are produced in reactors, some of them are produced in cyclotron, synchrotron, or using particle accelerator. So that radioisotopes and some of the radiations that they are emitting, these two are used enormously in various industries. The spectrum is huge. You can, you will be able to get the idea at the end of the lecture that there is no field remain in this today's world there where radiation is not being used. So for ease of okay. So for ease of understanding and ease of presentation, I have divided the applications of this in different industries in some groups. So first you can see the major and foremost part is in nuclear power industry. So the fuels that we are using in nuclear reactors, they are radioisotopes. Some of the materials that are used in reactor, those are also radioisotopes, some elements. So these are main use of nuclear reactor, and from nuclear reactors we are getting different isotopes afterwards that are used further. Then in yesterday's lecture, Tapas Das sir covered very well the medicinal and healthcare industry, where radiation and radioisotopes are being used. Majorly in radiotherapy, brachytherapy, diagnostic, nuclear medicine and sterilization. So I will be covering a small part in sterilization. It was left yesterday. So how radiation is being used in sterilization and how it is generating a huge amount of what do you say, industry. It's a big value industry of today's world, the sterilization part only. It contributes almost more than 50% of the revenue that whole radiation industry is generating. Because the field is explored much well, it is a very old field, the sterilization using radiation. And then radiations and radioisotopes are being used for various environmental applications, to treat wastewater, to treat flue gases for various industries. And then we have application in agriculture and food industry, and there is application, the major application, all the except all the radiations, gamma and electron beams are mostly used for radiation processing. It can be processing of food, it can be processing of some polymeric material for generating or development of some new super material that can be used for various applications. And then we have application of isotope in isotopic hydrology and radio tracer technology. So radio tracer technology is also been covered by Sitaraman sir and Tapas sir yesterday. So as you are aware that nuclear reactor, this is very well covered by Sitaraman sir yesterday. So there are different types of reactor. There are 3-stage program we are in nuclear program. So in different phases, different isotopes are being used, and it can be categorically divided into this way, like each reactor is having different kinds of fuel, and different kinds of fuel means different kinds of isotope and different setups of whole. The setup will be different for each kind of reactors. So in all the cases we are using radioisotopes. So this is an example where radioisotopes are used in nuclear industry. And then medicine and healthcare industry, I will not spend much time on this. Tapas Das sir explained very well what are the applications of radiation and radioisotopes in radiotherapy, diagnostic radiology, nuclear medicine and sterilization. So there are external beam radiation and brachytherapy. So these two are, as the name suggests, external beam radiation. So here the radiation source is away from the patient, away from the body. And in brachytherapy, it is just opposite. The radiation source or radioisotope is very close to the patient. And the isotopes which are used, radiations which are used for EBT, radiation which isotopes are used for brachytherapy. And then I will spend some time in this slide. This is a high energy electron accelerator. So apart from gamma or beta emitting radioisotopes, electron beam accelerator is also being used nowadays for treating cancer patients or in medical industry. So they are high beam, high energy, but this is also being used from external beam therapy. It comes under external beam therapy. But as you are aware that electron beam has less penetration power, it is like a beta ray, so it cannot penetrate much. So electron beam therapy, electron beam accelerator therapy can be used only for our outer treatment. Like if I have a tumor in my hand or in the outer surface of my body, then that can be treated by electron beam accelerator therapy. And there are these are the 5 centers where electron beam accelerator is being used for treating various kinds of diseases, specifically cancers, in the Jai Vigyan mission of Government of India. And you can say that in cases, mostly yesterday lecture was covered by gamma sources, telecobalt sources for therapy. And this is the advantages and disadvantages of accelerator and gamma rays. So in accelerator you can tune the energy. If you need very low amount of energy, using electron beam accelerator you can tune that energy. But if you are using gamma ray or any radiation source, the energy is fixed. For a certain kind of isotope, the amount of energy it emits, that is fixed. So you cannot tune the energy. So that is one major difference using these two, and there is very less amount of safety concern related to electron beam accelerator, whereas for gamma therapy we need to have better or more safety precautions. Then diagnostic radiology also, there are many applications of radiation and radioisotopes. And nuclear medicine, it is well covered in yesterday's lecture. These isotope is very common to you now, technetium 99M, iodine 131, iodine 125. These are used in nuclear medicine as a imaging or as a therapeutic agent. Then I will come to the third industrial applications of radiation and radioisotope, that is environmental applications. So environmental applications can be categorically divided by 2 parts, like some wastes like wastewater containing dye, wastewater containing sewage sludge, that can be directly radiated So, amount of pathogen or amount of antibiotic agents or amount of dye that is absorbed or that is contaminated the water, that can be degraded using the high energy ionizing radiation, and the water will be clean. That is one approach. And second approach is by development of some absorbent or some membrane using radiation technology which can separate the pollutants from water. So, by these two approach, mainly applications of environment is controlled. Now, you can see this is an example, this technology is development by BRC RTDD. So, here they have done, they have attached grafting. You are aware of grafting. Normally it is a old method when we used to do in nurseries, means plant. In agriculture, grafting is very common method. Like if I want to have a good fruit, and we have one mango tree is having a good fruit, but its stem is not very strong. There is a very small tree, it cannot hold much amount of fruit in that. But another mango tree is having good root intensity, good strength, but its fruit quality is not good. So, if I can graft these two, then I will have a mango tree with better root strength, better stability with good fruit quality. So, this is a basic concept of grafting. The same way, by using high energy radiation, we can graft a different kind of molecule onto a different base material, that is polymer, that can be a substrate also. Like cotton, this work is based on cotton fabric, that is a normal cotton that we are using, the banyan or the t-shirt we are using. So, that is made of cotton fabric. So, that cotton fabric is being grafted by some certain molecule that is having affinity towards dyes, specifically anionic dyes. So, then it has become an absorbent of anionic dyes. Then this setup is being used for cleaning various textile dyes, specifically anionic dyes, and then this technology is now set up pilot scale in Rajasthan, and Rajasthan Pollution Control Board has consented to set up 2 such plants in different textile industries. So, this is an example where we are using radiation passively by developing one material which will be helpful in environmental remediation. Now, second one, this is a work here, polyurethane absorbent, polyurethane like the mattress, the sponge that we use in our mattress. So, that is polyurethane. So, huge amount of waste is generated because the waste mattress is sent to dumping yard, and it is not biodegradable, it remains for years after years. So, we can use that scrap polyurethane and we modify it using radiation, so that it can separate toxic organic material from water surface. So, this also can separate toxic material. So, it is having the potential to be used in environmental remediation. So, in this picture you can see this is a oil, the red one, it is a dyed oil, and this is a mixed with water. So, it can selectively separate the oil from oil water mixture. So, it can have wide application in separation science. So, these two are passive application of radiation. By using radiation we are developing material, that material is being used for environmental remediation. Now, this example is a sludge hygienization research irradiator. This is located in Baroda. This has been commissioned in early 90s, I guess. So, it is being used for last 20-25 years very successfully. What here we are doing, here the sewage sludge is being irradiated. It is being packed in different baggages, and it is given a certain amount of gamma dose. Gamma dose why we are using? Because it is having good penetration capability. So, sludge we have in big bags. So, it is a very thick, like 15-20 centimeter of thickness. So, we are doing double side irradiation. So, high energy irradiation, when it is impinging of the sewage sludge, it is killing the pathogens and bacteria. And then this has been some nitrogen agent is being added to that, and this is being used as a manure. Then it is sold in packets for local farmers and it is being used as an So, then you can see, and this is being the same kind of plant has been now is operational in Ahmedabad Municipality Corporation, and one such plant is coming in Indore in very soon. So, this kind of plants is helpful to manage the waste we are generating in certain areas. Like Rajamundry, if you are generating what amount of sewage and sludges, that is going to your river by some way or by another way. So, if we can set up such a plant, so that all the sludges can be treated and that can be used as a manure. So, you have a very good land. So, this land can be even the fertility can be improved by this kind of technology. So, this is having good application in industrial sector. Now, you can see I said that it is a gamma plant because the thickness is very high. I am irradiating the sludge in bulk. Now, same thing we can do using electron beam accelerator, but as the penetration is less, So, we need to repack it, we need to make the thickness very thin. But the benefit with electron beam is such that it is having very high dose rate. Very small amount of time we can give a large amount of dose. So, my processing time will be very less. In a single day I can give a dose that a gamma plant can give in 1 month. So, that is the difference. So, this kind of technology is also in the forefront and research works is being done. So, it is having beneficial compared to gamma in some aspects. So, depending upon the material that we are using for environmental remediation, we have to choose which kind of isotope or which kind of radiation we will use. Now, this is this slide I have taken from this source, and there they are doing the flue gas treatment. Various industries emit different kind of gases, toxic gases, various sulfur dioxide, sulfur oxide, NOx and SOx. So, they directly goes to the environment and they cause tremendous amount of air pollution. So, by attaching electron beam accelerator in the channel, if we can irradiate the flue gas that is coming out of the reactor or coming out of the furnace, that toxicity can be reduced, and if we add some ammonia kind of agent into that, that can be converted to ammonium sulfate or ammonium nitrate, which will having added revenue generating or value added product. So, in this figure you can see this is a boiler, this is a reactor. So, all the fumes that is coming from this plant, it is being transported to this channel, and here this is the electron beam accelerator. This is number 11 that you see, it is at the end. So, all the fumes that is generated by this plant is being irradiated and it is then released. So, it is controlling the pollution, and some in some channel there is a option of adding some ammonia or some active chemicals that will make these gases even more beneficial in terms of value addition. So, this kind of plants we do not have in India now. This is a plant in China, and this is a report by Andres Kemlewski. Okay. Then applications of radiation and radioisotope in agriculture and food industry. So, agriculture and food industry is highly beneficial if we can use the radiation and radioisotope strategically. The two way we can utilize radioisotope and radiation. The one thing we can do, this as you are all aware that we are the largest producer of food, but only 2% of total food that we generate is being processed. All the foods, all the plants, all the agricultural products are being maintained or managed naturally. That is why 20 to 40% of our agricultural productions is spoiled due to insects, pests, microbes. So, you can imagine how much waste we are doing, which is very wealthy thing. Agricultural products, almost half of the products are being wasted because of these factors. So, it is around 35,000 crores of loss annually, and this value is long back, it is around 2020. So, the value would have been almost increased in double or triple. So, some using irradiation, if we can preserve the food, agricultural commodities, if we can hygienize the food packets, so we can improve the shelf life of the product, we can reduce the waste that is generated, and even we can export the material, export the food item, export the agricultural product, and we can generate huge amount of revenue. So, this is one approach by radiation processing. So, we will give radiation, certain amount of radiation by certain radioisotope, and it will improve the shelf life, it can kill the bacteria, it can kill the pathogen that is causing the damage of the food after a certain time. And the second option is mutation breeding. Mutation breeding is like some seeds or some crops we have, by tuning the radiation dose, we generate a different kind of variety of that food products, of that plant or of that seed. So, it will have property, better property compared to the parent one. It will have, you see, it can have that it crops mature early. Like for normal paddy, if you are planting, it may mature in 3 months or 2 months. If you use a certain amount of crops variety, it will mature early. So, in a year, if you are planting 3 times, you can plant 6 or 7 times. Then it can withstand biotic and abiotic stresses. Like certain amount of foods are very prone to microbial attack, some pest attack. So, if we use a certain crop variety, they will have the inherent capacity to withstand the resistant this kind of infection or pathogen related effects. Then we have also we can have better nutritional value. So, this is also this mutation breeding is a trial and error kind of thing. certain research we have to do for a very long time, then only we can produce a certain variety of mutated crops. So, conventional method of food processing, you are all aware what we do before monsoon, we all used to do, our parents or grandparents used to do, we sun dry our cereals, dals, our wheat, we sun dry and then we pack closely. But we do this because the by sun drying the attached moisture gets evaporated and some sort of bacteria or pathogen or whatever is there present, that will be killed by the radiation, that high sunlight radiation. So, what is the problem with sunlight is that its penetration is very low, it cannot penetrate much. So, we cannot irradiate any food item in bulk. So, we have to spread it, we have to make a monolayer. So, by this sunlight processing, we cannot process the amount of agricultural product that we are generating annually. So, we need to have a sophisticated, fast and high throughput process. By that we can irradiate or we can preserve the food in a large quantity. So, in that case our radiation is very helpful. Other processes that is available is some chemical treatment using ethylene dibromide, methyl bromide, phosphine, etc. But after processing with this kind of chemicals, there will be chances of some chemical contamination in the food, that madam was asking yesterday. So, this kind of there will be chances of chemical contamination, so that is not very healthy, and this process needs high temperature. So, some kind of fruits or some kind of food products you cannot process at high temperature, like fruits, mango, you cannot irradiate at 120 degrees centigrade, it will get spoiled. So, for that cases radiation is a very good option. By radiation processing we can solve this kind of problem. Like it, you see the radiation processing, it kills uniformly the developmental stages of pathogens, insects, even within the grains. It leaves no harmful chemical. So, it does not need any further treatment or any successive treatment. Once you irradiate in a packed condition, it is ready to store for months. It can be applied for pre-packed food. So, it is ready to market, ready to transport. The process is environment friendly, it does not need temperature, high temperature. So, it is sensitive, does not sensitive to the food products or agri products that we are irradiating. Then you can see that cobalt 60, cesium 137, X-ray from different machine sources and electron beam accelerators are being used to irradiate different kinds of food depending upon the suitability. And any food that is being irradiated or is marketed after irradiation, it will have this symbol. This is a radura symbol. This means the food product that you are consuming has been irradiated by some kind of radiation. Yeah, so now we will show some slides from our food technology division. They are doing enormous amount of work in this field. So, there are government approved food products that can be irradiated like onion, potato, ginger, garlic, spices, etc. And you see this is a mango I was talking about, because mango we cannot treat it in high temperature. So, in gamma radiation, if we irradiate mango, the quarantine application is very helpful. Like sir was telling yesterday that we cannot export mango to USA without quarantine irradiation. That means we have to kill all the bacteria and pathogen that is present in mango. And during this process, we have seen this data, you can see this is the mangoes at day 0, then after irradiation day 12, 25 and 35. So, up to 35 days there is no significant or notable change in the mangoes after irradiation. So, the shelf life is increased, the bacteria pathogen that was present, that has been killed by the radiation, and the value has been increased, because now we are able to export into other countries. The same way this is a date. So, you can see after 40 days of irradiation, the irradiated food showing no symbol of spillage or any damage in the quality, but you can see the control food, it has already been spoiled. Yeah. Now, some example I will be showing of mutation breeding that I was saying. So, you can see this is a groundnut variety of TG51, a very high production rate, very big chunks, like groundnut is denoted the quality of groundnut, how many groundnut you have in a single piece of groundnut. So, more the number, better the quality. In market if you go, some groundnut will be having only one dana in that. So, that is not of good quality, some will having 2. And if it is having 3 or 4 dana, sing dana or that mumfali inside that, that is of higher quality, that is of premium quality, it will have more value. So, this kind of crops variety if we cultivate, we will have a better product, better yield, and our farmers or our agricultural workers can earn more revenue. Similarly, this is a a photograph of a rice variety. You can see of the stick air column variety which grain, it is having longer and whiter rice compared to the control one. Similarly, almost 70 types of crops had been developed by DAE. Here are some example. I have put this TG47. This is released, this crop, this commercial cultivation has been released to Andhra Pradesh in 2011. So, maybe which what simdana or that groundnut you are having, that may be of a product of TG47. So, you are all beneficiary of radiation and radioisotopes. So, this is of what you see, the large seed is maturity days is 110 to 115 days, normally it is more than 200 days, normal general groundnut, and this crops is having lower maturity time. So, you can cultivate more number of fruits, more cycle you can do, and then it has more than 3 seeded pods in that groundnut. Similarly, there are this kind of thing, then there is a mung bean green gram that is released in Andhra Pradesh in 2017, TM962. It is also resistant to certain kind of pathogen or infestation. Then it was, I used to know it was a 60 trombe crops variety, but after Daniel Babu sir's presentation day before yesterday, we came to know the number has increased to 70. So, total 70 number of crops variety has been released, and the data I have shown is the source are listed here. So, now you see the industrial application of radiation processing. So, apart from environment and environmental remediation, food and agriculture, nuclear reactors, there is a fifth application is industrial application of radiation processing. So, mainly in processing we are using gamma sources, cobalt 60 and cesium 137, because its energy is high. You can use other gamma, but energy is low. So, I cannot irradiate a bulk sample using that gamma. That is why we are choosing cobalt 60 and cesium 137. If you note all the plants, all the irradiator that I have shown earlier, all are based on cobalt 60, because its energy, its penetration is even better than cesium 137. Cesium 137 also we are using in some irradiator where you need low dose, total dose is low, like blood irradiator. We are using cesium 137 for that purpose, and we are using electron beam for various radiation processing. Okay, so you can see this is just to give you an idea how one gamma chamber or gamma irradiator looks. This is a small gamma chamber. The size, this we keep sample in this holder. The sample chamber you can see, this is the sample chamber. So, this is a small gamma chamber, very tabletop like this, this plot, it will become into this size. So, sample size is 2 liter. We can process 2 liter volume in that chamber. That is for research and developmental works only. So, and the next one you can see, this is a schematic diagram of radiation processing plant that is situated in BRIT, Navi Mumbai. So, this is a large scale plant, it has a capacity of 1000 tons irradiation per day, and this is the dimension of the box. We have to put the food or agricultural products that we are going to irradiate in this tote box. This is made of aluminium, and this it is a conveyor, rolling conveyor is there. So, you have to load it here, it will pass through and it will have some cycle, and this is the source. Here it is getting 80% of the dose in this cycle only, and it gets some 10, 15, 20% in the process. So, and it comes out of the chamber and it is then sent to the vendor after proper irradiation. And this is a chamber, this is a gamma irradiator, mini gamma irradiator recently developed by BRIT at Vashi complex. It has chamber size of 150 liter. So, this is like a batch pilot plant. If you have some product you have done in gamma chamber very small scale, then you want to see whether how it works in a medium scale, you can use this gamma chamber. This we are using for our different kinds of work in DAE. So, this is having 200, and for large scale this gamma plant, this is on payment basis. Different industries comes to BRIT Vashi for irradiation of their products, specifically spices, different kinds of pet food, etc. And this is ILU EBA, this is electron beam accelerator. This is also located in BRIT Vashi. This is a BRC establishment, and this is our electron beam horn. So, the electronic setup is there in the next slide you can see, and we can irradiate the sample if we put below this horn. So, the sample size is 8 centimeter by 100 centimeter, and the conveyor is moving. So, you can irradiate any size of sample. The maximum size can be 100 centimeter, that is 3.5 feet, and it is in rolling conveyor mode. So, sample can be come and go, and it will be any size of sample you can do. The only constraint of electron beam accelerator or electron beam processing is that its penetration is very low compared to gamma. Gamma can penetrate in meters, it can penetrate few centimeter. The thumb rule is that if your electron beam energy is E, So, it can, the utilization thickness is E by 2 in centimeter. So, if you have a accelerator of 5 MeV, so it can utilization thickness will be 5 by 2, that is 2.5 centimeter. So, only 2.5 centimeter material I can process by single irradiation. If I again do double side irradiation, then it will be 5 centimeter. So, that is the constraint, and there is many other advantages also. As I said earlier, that it will take very less amount of time to distribute the dose. It is very fast process, throughput is very high, radiation safety and other precaution is less compared to gamma, as it is a machine source. If I switch on the machine, if I operate the machine, then only there is radiation, otherwise there is no radiation. But in case of gamma, whether I am utilizing my plant or not, the cobalt 60 or cesium-137 will be emitting gamma. And this is some few more figures. You can see this is a graphical design. The beams are coming from this top, and this is a movable conveyor. The material of interest, we put it here, and this is irradiated. We have to do proper dosimetry, what dose it is getting. Okay, this is a design, and this is the conveyor, rolling conveyor. We can do in continuation mode also, like the gamma plant. Yeah. So, what radiation is doing, what radiation processing is doing into our material. So, if you recall the first lecture of interaction of radiation with matter, you may be aware that it ionizes, because it is having energy very high, ionization energy, it is a ionizing radiation. So, once it ionizes the system, then due to some internal reaction, it forms radical. Radicals means it is having an electron, unpaired electron over the molecule. Then it has an option to cross-link, it has an option to degrade. If there is any monomer is present, like I was saying during that food products mutation, that is a grafting, it can also graft. So, I have a matrix here which is like A. If I put a monomer B and I irradiated it, if the two are reactive to radiation, then I can get AB. So, I will get the property of B, A will be retained, and additional property of B I will get. So, I will get both the property of A and B. So, we have to select the molecules such a way that we get the benefits of A and B. Similar way for polymer and specifically for polymers, cross-linking is very beneficial process. Many of the applications are based on cross-linking only. What cross-linking does, if you see this figure, like this was the chain of polymer. Now, after radical formation, there is interlinking. Number of bonds is increased in this. So, number of bonds is increased means the material, the matrix has become very tough now. Their mechanical property is increased. It has become strong, like that. These two are my polymer chains. If I irradiate, if it is a cross-linking polymer, these two will bond. So, this is stronger than these two, right? The same mechanism it follows. And some kind of material are not radiation stable, they undergo degradation upon radiation. So, we have applications based on degradation also. If it cross-linking, there are many applications. If it is degrading, there are many applications. If it is grafting, there are many applications. So, first we will go through the cross-linking, application of cross-linking. So, if we understood that it is improving the property. Once there is a cross-linking, we are cross-linking any polymer, it will improve its mechanical property, it will improve its chemical stability, chemical inertness, etc. And here are some products that is developed using radiation cross-linking. These are plastic parts, wire and cable for high temperature use, because the not irradiated polymer parts will not have high temperature resistance. But after cross-linking, as number of bonds is increased, it has become tough, the mechanical property is increased, chemical resistance is increased. So, now it can be used for high temperature use. Similarly, O-rings and gaskets that are being used for reactor, even for thermal reactor, different plants where high temperature is involved, there the gasket needs to be stable during the operation period. So, service life is improved. We can increase the service life of gaskets and other polymer parts that is being used in harsh chemical condition, where if we use the pure polymer, that cannot withstand. So, frequently we have to change that. But if we process with radiation, if there is cross-linking, then that kind of material will have added beneficial property. Then I was saying that the degradation is also having some applications, like Teflon is a polymer that we all use in our non-sticky frying pan, that is a coating of Teflon only. Teflon is a very inert material. It does not absorb water. So, it is very non-sticky. That is why very less amount of oil you need if we fry in frying pan, because interaction is very less. It is very inert. But what happens? It is inert, but if you place PTFE scrap or PTFE under radiation, after 100-150 kg of dose, it becomes powder. It degrades. So then degraded Teflon has other use, like we use in paints. Nowadays various paints have come, no? Oil repelling, water repelling paints. So if you add this Teflon powders into paint and you paint your wall, it will be weather resistant. So it is also having some added beneficial property, and it is a very high value product. And color center generation is also another advantage of high, as it needs high radiation, very high radiation of few thousands kilogray, 1000 kilogray, 1500 kilogray, and the thickness is not high. Any precious stone, if you find, it will be in few mm. So this is done by electron beams specifically, not by gamma, because the dose, amount of dose we need is very high. So you can see there is some, this is unprocessed, this is of diamond. So unprocessed diamond, the cut diamond that we are using, that is having very less value. The bigger the size of diamond, bigger the crystal, higher the value. But during processing, so there will be some cuts, very micron or small amount of diamond that is discarded, that has no use. And as it is very small in size, that value is decreased. But if we irradiate that white diamond, cut diamond, very small size of diamond, using radiation, it becomes colored depending upon the dose. At certain dose it will become pink, at certain dose it will become green. So now this colored diamond, even if the size is small, has higher value compared to the that white one, colorless diamond. So this is a very high, big revenue generating industry. There are numerous plants operating in India, specifically in Gujarat, Surat, in that border. They are irradiating these cut diamonds and they are making it colored, and depending upon the suitability and demand, they are supplying these diamonds, irradiated diamonds, to various industries. So this is have a very futuristic use, diamonds industry. Gold has become diamond now. The price of gold has become almost like a diamond. So this diamond industry has having very good future in industrial applications in future. And like yesterday, sir covered all the parts, only the sterilization thing I will spend some time to explain this. Sterilization is being done by radiation. It is mostly done by gamma, because we need high penetration. But if the sample thickness is very less, we can sterilize using electron beam as well. What it does, sterilization, it means total elimination of pathogens and virus from the material that is being irradiated. So various medical supplies, surgical scissors, etc., gloves, surgical gloves, apron, used aprons, those are being sterilized using gamma ray, and the total amount of dose, approximate amount of dose that is needed to have the effect of sterilization is 20 to 25 kilogray. So it is having some advantages because it does not need any high temperature, it is a cold process. So heat sensitive material can be sterilized, deep penetration power, it is homogeneous, all the parts will be sterilized properly, which is not possible by using some chemical methods. It does not leaves any chemical toxic residue, so there is no quarantine or cooling period. We can use the material as soon as possible, as soon as the irradiation is done. And also the grafting I was talking about, there are huge and numerous application of radiation grafting. It has application in tuning the surface wettability, it has application in preparation polymer blends and composite, reduction of friction, development of antibacterial surface. So the property of the monomer will determine the application of the grafted polymer or grafted material. So if you want to prepare, like the first example you remember, that cotton that is used for dye absorption. So in that cotton, normal cotton cannot absorb dye, the pure cotton, pristine cotton, but we have grafted a certain kind of molecule that absorbs the dye molecule. So the grafted cotton can now take up dye, it can purify dyed water and it makes it colorless. So the same way, the amount of monomer, the kind of monomer we will select, that will determine the end use of the grafted matrix. So some example I will be showing you 2-3 examples in a very short way. So there are advantages, this is the list of advantages that I have in radiation processing compared to the conventional thermochemical process. And this is one example where we have developed one radiation resistant modification. We have made this sample and EPDM we have grafted with different acrylic acids and acrylate, and we have found that methacrylic acid grafted EPDM is having anti-fouling property. It does not foul if we keep it in water medium for long. Then another example, if you see that polyurethane sponge that is used for environmental remediation is being prepared by radiation grafting. Then there are various polymer blends and polymer composites. The property, mechanical property can be improved by radiation cross-linking. Here we are doing cross-linking also. And this is an example of preparation of polymer composite. Like natural polymer composite, if you see, polymers are hydrophobic in nature. They are mainly plastic, hydrocarbons. Now if you want to make composite with some non-polar media, then it is not very compatible with that. Like you see the concrete we are using, cement and rod we put, the steel bars. If these two are not compatible, our ceiling or our roof will not be very strong. So to improve that interaction between the polymer and the natural matrix, the radiation grafting is very useful. And this various kinds of surface wettability we can tune, and as per our application we can use this kind of material for various applications. And now I am coming very close to the presentation, the isotope hydrology. Here we are 18% of global population, almost 20%, and India has only 4% of world's total fresh water. So 20% of population has to manage with 4% water, and in most of the cases you are blessed with ample amount of water of Godavari, especially Rajamundry people, but in cities, metro cities people, there is water scarcity. So 37 to 40% of water sources are being overexploited. So we need to handle this problem with very care, and isotope hydrology is the solution. It is a very useful tool, very useful method. So using this method we can check whether isotope fingerprints is the method, groundwater recharge and dynamics. Groundwater, if the rainwater is not recharging your groundwater, then there will be scarcity of water. So by using isotope hydrology we can check which is the charging point, and in that point if we make some lake, if we can manage to make some rain harvesting method, then that rainwater will go and it will recharge the groundwater, which will give us, again we can use that water for our purpose. In the same way, geothermal sources can be checked, hydrographic separation, surface water, groundwater interconnection. Like we visited your dam yesterday, day before yesterday, is a very beautiful dam, but I am told that at certain point it is meeting with the sea. So the salt water is getting mixed with your sweet water. So it is not edible. Now you cannot use that water. So it is possible by using isotope hydrology to check at what point the sea water is mixing with your drinking water or sweet water. So in that, using isotope hydrology, then you can do some mechanism, some creation of some slant or some dam, so that your water loss will be minimized. So there are the isotopic hydrology studies is done whole nationwide. You can see almost 40 to 45 projects are being done by our colleagues in different parts of India. And there is application of radio tracer application in this industry of radiation, isotope and radiation. As the name suggests, tracer. Tracer means trace amount. We have to add trace amount of radioisotope in a system to check whether it is working properly or not. This is applicable in the place where we cannot actively or directly see the setup. Like we have a very big chimney of some 100 meter. Every point I cannot see. What is happening inside I cannot see. There is a canal, there is a pipe, gas pipe of some few kilometers. So where there is a blockage, if there is some leakage, I cannot see, I cannot check through manually. So in that cases, radio tracer technique is very useful. What it does a very incorporation of tracer amount of easily detectable material into the system to provide information about the whole system. It is a chemical compound added in a very small activity, and it gives unique information about the system which is not readily obtainable by any other means. So these slides I have taken from our colleagues of IRAD. And the purpose of radio tracer, as it says, is troubleshooting of any industry, optimization of process efficiency, it enhances the product quality, design process system. If there is some error in your design process, that can be minimized, processing scale up and quality control. Where it is applied, as I said, it can be applied where we cannot do it manually. Petrochemicals, the oil channels are very long, is very complicated. Oil and gas industry, chemical industry, wastewater treatment plants, automobile sector, glass production industry. So in that cases, we do not have any alternative, competitive alternative. So radio tracer technique is the only solution. In different applications, radio tracer technique has like leak detection, sediment transportation, flow rate measurement, particle tracking, thin layer activation, effluent dispersion studies, investigation in oil field, and densitometry measurement of phase fractions. These are some common radioisotope radio tracers that is being used in industry. And this is an example. This slide I think you have seen in the first day, Dr. Mahapatra's presentation. So this is a borosil plant. They had some 100 meter channel product line and there was some problem. They were not able to get a proper glass sheets. So, by using radio tracer technique they able to get to know that at some channel there was not, the mixing was not proper, that is why there was phase separation. So, they rectify it and it is working perfectly. In a similar way, this is a study done in VPCL, and here you can see using radio tracer technique the flow, there was a problem in the flow and that it is rectified. Flow rate measurement, like I was saying, this is similar like your dam. So, whether the flow measurement canal and pipelines are calibrated, flow meters are working properly, that can be checked frequently using radio tracer techniques. So, at the end I will say there is nothing to be feared, as Marie Curie said, it is only to be understood, and if we understood the thing we can be utilizing any dangerous thing, any kind of thing for our beneficiary, like we have to do for radiations. Okay, so I thank you all for your kind attention, your hospitality and your interest in radiation and isotope. So, if you have some query,
Any queries?
we can discuss.
Sir, diamonds are colored with radiation now, sir.
Yes.
So natural diamonds are artificial diamonds, sir.
Sorry.
Artificial or natural?
That diamond is to be mentioned. When we radiate some natural diamond, there will be colored diamond naturally also. You know, some diamonds are pink, that is naturally pink. But if you are inducing color after treatment, then we have to mention it. That is treated diamond. That certificate the seller has to provide. Otherwise, you will not be able to know whether you are buying a natural diamond or a treated diamond.
After coloring and it is going to the IGA and International Gemological Institute, sir.
Yes,
Certificate.
They will give certificate and it is long lasting. It is not like the color is generated and it will fade away with time. It is everlasting. But that is artificial. That is the difference.
Good afternoon, sir.
Good afternoon, ma'am.
Sir, what are the effects of EB? You have explained, like, what is the full form of EB?
Electron beam.
Electron beam.
Yes.
And what is paleo channel studies?
Paleo channel, like some rivers will be, it will be remnant. Like it was river, there was a flow long back. Now there is no flow.
Okay.
It is covered by sands or some obstruction. So we can check whether there is water inside that. So we can charge it. We can make that river flowing again. That is use of our isotope, radioisotopes.
Yes.
Sir, this coloration taken place because of the point defects or dislocation?
Yes, exactly.
Yes, okay, thank you.
Color center, that we call
Yes,
color center.
color center,
radiation.
yes, okay.
Sir, is there any radiation method to control pollutions of the rivers, sir?
Pollution of the river.
To control the pollution or to eradicate the pollution from the rivers.
Yes. Like
How to detect different kinds of the pollutant from the river?
Yes. By using radiation, as if simply you cannot detect which kind of what pollution is
Yes.
there. If it is known, like I shown one example where it is dyed water, textile dyes, they got mixed with our water resources, then it becomes colored. So using radiation, high radiation, if we put the dyes that is colored, that is a big molecule, aromatic molecule, that it will degrade and it will become colorless. That is one approach. And
Yes.
second approach is by using some absorbent. If you make some absorbent which will absorb that dye or that oil.
Is it possible to use amount of water like rivers?
Yes, that is being done. That dye plant that is that I have shown, that is being done for 100 kiloliter per day. That can be done.
Is it possible to remove the huge amount of the pollutants from the rivers?
River, you have to channelize it.
My question is that, is there any advanced techniques to identify which kind of the pollutants are present through radiation? Yes, that is my question.
But you should not be targeting river directly to eradicate the pollution. We should stop the pollution before it goes to the river. Right? It is of thousands of kiloliters of water. It will be very difficult to handle. If we stop it before it goes to the river, like your local water resource, it will be easier.
Thank you, sir.
Okay, thank you.
So now I welcome Dr. Yusuf Bas. Yes. And I welcome Dr. Yusuf Basha Garu for feedback on the session on applications of radioisotopes and radiation industry.
Thank you. Sir, the session is like a fast-moving thermal neutron, sir. It's going on, every slide a new topic, which we are unaware of it, and a knowledgeable session. Thank you very much, sir. We have came to know so many new topics actually. Under environmental applications, we have never heard about this Shri at Baroda, sir. The sludge hydrogenation research radiator, and so many things, not one thing, everything is a new topic only, and knowledgeable session. I think everyone has benefited with this session, sir. Thank you very much, sir.
Thank you, Basha Garu. Yeah. So now our next session is on radiation safety and setting up a radiological laboratory by Dr. P.S. Ramanjanelu Garu. Now I heartfully welcome Ramanjanelu Garu to proceed for his lecture.
Thank you. Okay. Yeah, good afternoon to all of you. Yeah, from last 5 days, we are learning so many things about the fundamentals of radioactivity and decay series, how it is, why it is some of the nucleus are not stable, and you are seeing something what types of radiations are emitting from the nuclides and its interaction with matter, and then detection, and some of the applications of nuclear technology like nuclear reactors, and then the production of radioisotopes and its application in various sectors. From last 5 days we are learning. Now today we are entering to the last lecture, technical lecture of this our workshop. Now I just want to clear some of the misconceptions about your radiation and how to set up anything laboratory in case if you require anything, want to do something research by using something radio tracers, how to set up a radiochemical laboratory in your own laboratories, how to convert basically your own laboratory into as a radiochemical laboratory. Okay. Now before going to details, the many people thinks that what are the dose we are getting by handling something radio tracers are very dangerous. So compared to what the natural dose you are getting from the radiation sources naturally available from the radioisotopes, compared to that what the dose we are getting by using the radio tracers are very negligible. Okay. Now of course I can't say that radiations are very safe to handle. The way when the late 80s when they discovered the power in AC alternating current, at that before that everyone is using the DC current. There is a misconcept that if the AC current is there, if you touch it then everyone will die like this. But now you see with precautions we are using, now you imagine without the life of using the power, AC power. Now wherever we have from long distance we have something power plants, and today we are getting in the Rajahmundry in this auditorium power, that is because of alternating current only. If you could have with an AC, DC current, we can't supply this much long distance. The same way, if you understand what the mechanism and if you follow something safety protocols, then definitely radiations are much better side if you go for an application side. This is what I want to say in the coming few slides. Okay. The natural background radiation. The natural radiations are the main source of radiation exposure to the general population. Everything in our environment, including the food, as I mentioned, your own banana has a lot of radiation that contains trace amounts of radioactivity, and the natural sources can be classified into external sources like the extraterrestrial origin like cosmic rays, it is coming from the sun rays, and then terrestrial origin like potassium 40, uranium 238, thorium 232. These are our naturally available radioisotopes. Or some of the like internal sources also, the radioactive nuclides occurring in the biosphere enter the human body through the injection or inhalation. Suppose someone is making something potassium, something plant, if it is in airborne, if you inhale it, that may enter into your body, that also create the something dose in your internal. Now the natural radiation sources, we are exposed to the radiation every day from the natural background like such as cosmic rays, and then whenever they are doing something mining and other things, some of the radon gases will be released and then we are inhaling from that. And there are something internal, because when we take something banana or milk, anything, the potassium we are injecting into our body. And also if anyone is inhaling, the definitely it contains some of the radon gases which are naturally releasing from this. And then what the food we are taking, suppose if we are taking something potassium rich foods, it may give something additional radiation also. These all are natural radiation sources. Inherently every one of these present in this auditorium, everyone is taking, but we are not aware of that. But when you movement to say something, use the application of any radio tracers, we all are fear that something radiation is coming. From compared to this, what we are getting those from the sources are very low. This is what I want to say. The radioactivity of some of the natural and other materials, if one adult human being, if you take around 70 kilograms weight, then we get the something radiation about 7,000 becquerel. Like if you say 1 kilogram of coffee, the coffee also contains some of the potassium, it is giving about 1,000 becquerels. And 1 kilogram of any superphosphate fertilizers, whatever we are using in that, is having around 5,000 becquerel. There are so many sources. These are some of the examples I mentioned here. In addition to this, if you go for anything traveling by flight, then you will get, because of the UV radiation or cosmic rays, you will also get the radiation. The largest contribution to our dose is from natural background, that is about 2.4 millisieverts per year. This is on the average. Some maybe places have the higher dose and some of the places may be lower dose, but on the average we are getting about 2.4 millisieverts per year. Okay, the cosmic rays dose, suppose someone is traveling on the flight from the Los Angeles to Paris, then they will get the dose of about 48 microgray. Okay, in Chicago to Paris, they are depending on the travel, how much time they are traveling, and then area, then they have the dose rates are different. So what I want to say, if you would travel by flight, you will receive more dose than standing in front of any nuclear reactor for like hours together. The man-made sources of radiation contributes the radiation dose about average 0.6 millisievert per year. This is man-made means like that someone is heavily smoking, the tobacco contains some of the radium, and the decay product like polonium will also emit from this smoke, and then who are taking the smoke inside, that they will get some of the doses also more than us. And if anyone is traveling by flight, then he will get something like 0.1 millisievert per trip if you are on the average around 3 to 4 hours traveling. And also the building materials, because they are using so much of sand, that also contains many of the naturally available radioisotope that are also give the dose. And some of the time fallouts, because of there are so many nuclear tests have been carried out in the past, that maybe some of the fallouts are also will be there, that also giving some of the dose like 0.01. During the earlier decades, the mankind was afraid of fire. Till recently there was a fear about the usage of electricity. We all of you know that, but still we are using the fire very conveniently to cook our food and many applications, the same way what the power we are using for all our applications. However, in modern life these tools have become handy. The user has learned to treat them as friendly applications. The same can be told about the applications of radiation or radioactivity. The way we are given the respect to our AC current, the same way you give the respect to our radiation, then we can apply conveniently for our applications. Okay. The taking proper care during the uses of radioactivity shall lead to its advantages. The applications of radiation have grown vastly in the fields of agriculture, medicine and industry. Maybe now you are knows better than us about the what the applications of these all radio tracers in agriculture, medicine and industries. I hope. Presently we are using the varieties of radioisotopes, radiation sources that are in each direction, are detection, diagnosis, cure and everything. However, the term radiation is viewed with fear because of its ionizing nature. Still we have some of the concept that whenever somebody say the radiation source is available, we have something with fear only we are treating them. Now the radioactivity should be respected, not to be feared. This is what I want to say. The radioactivity is an invisible event, could be sensed by only suitable detectors, and it is defined as the process of emission of high energy radiation by nuclei of higher or unstable elements. Because the radiation cannot be viewed by our naked eye, it has to be sensed by using some of the detectors, the way you are using like GM counter or sodium detectors. Now there are 3 types of radiations. I hope you all of you know by this time: alpha particles, beta particles, and gamma rays. Then one of the girl is also already asked about the alpha particles. Penetration power is very low, do not pose any radiation hazard, can easily be prevented, just like one thin paper can be stopped this. The beta particles pose radiation hazard only if their energy is higher, and the gamma rays can penetrate some of the air into some meters, and the neutrons can also penetrate. The occupational exposure, the external exposure, the source of radiation lying externally, exposure can be controlled. Suppose you are using something radio tracers, some gamma rays are coming from that. By using some proper shielding, we can control what are the dose we are receiving from these external doses. Then internal exposure, we have to use minimum precautions such that the aerosol activity should not enter to your common laboratory and we should not inhale into our body. With minimum precautions, we can use conveniently depending on your application. The external occupational hazard, the radiation sources of high energy like hard betas, gamma, neutron, proton, heavy ions. This due to low linear energy transfer, they travel in air directly and irradiate the person. Okay, these all high radiation sources can ionize the air and then it can damage your body. The countermeasures, the distance, if anything radiation direct contact, though something like that 1 MR, if you go for 1 meter, that will drastically reduce your dose whatever we are receiving. The intensity of radiation exposure decreases as the square of the distance. If every 1 meter the square of the radiation can be times, we can reduce it. The time, the intensity of radiation exposure vary as a function of time. Obviously all of you know how much time we are spending very near to the dose, that depends on the radiation what you are exposing. If you require really to very close to the source, then only you be there, or otherwise just keep the source and from far away also you can see do the practicals or any applications. And then shield, the intensity of radiation exposure decreases with the thickness of the shield. We can use something shield such that the intensity can be minimized. The radiation protection, like as I mentioned, the time as minimum as possible you spend very near to the sources such that as low as possible we can achieve, and then you maintain the significant distance such that the radiation dose can be minimized, and by using something like proper shielding we can also reduce the what are the dose we are receiving from the externally or from the radio tracers or any applications. The internal occupational hazard, the route the entry by inhalation or injection, this all internal hazard we are coming, it is because of either inhalation or injection. You take a minimum precaution such that it could be avoided, like alpha radiation due to high LET, the radially stopped by air, hence not an external radiation hazard but an internal hazard. If anything externally you are handling something alpha sources, it cannot create anything problem for you because it cannot create any external dose. But if suppose it is gone inside your body, that will give the maximum dose because of very high LET powers. They get concentrated in some organs and tissues, depending on their biological mechanism, metabolism, whether where it is occupying more time, then that particular organs will get more dose. The irradiation of the cells takes place till the radioisotope get eliminated. Our body mechanism have something like that, biological half-life, depending on your elements what you are injecting, depending on your metabolism, that will be eluted out from your body. The effect of radiation, the radiation produces biological effect by in 2 mechanisms, directly the dissociating molecules are following the excitation or ionization. Because when a high energy you are depositing in your biological molecules, it may dissociate your biological molecules and it may ionize or excite. The indirectly by the production of free radicals and H2O2 in the water or body fluids. Because our 70 or 80% of the body is nothing but water, it will give something like it will create the free radicals and it may form the H2O2 that may spoil your metabolism or biological activity. Second one, the directly dissociating, because suppose of some alpha source has gone to your body that is emitting, that high energy you are depositing in your body, the biomolecules can dissociate, it will split. Okay, and then see, when you go something alpha particle energy is low getting lowered with interaction, then energy is so low, it may excite something, imagine something else. Yes, electrons will be there that will get excited, and it may get ionization also. Yeah, these are our history, who had discovered the radioactivity and effect of what they defined, what is the dose and everything. Just I mentioned here. The radiation units, the unit of radioactivity is becquerel. The 1 becquerel is nothing but 1 dps, means 1 disintegration per second. And you know what is the unit of Curie? The 1 Curie is nothing but 3.7 into 10 power 10 becquerels. In case of radiation exposure, the following units are in use, like Roentgen, Rad, Rem, Gray and Sievert. Some of the definitions I will mention here. What I want to mention here, whatever the uranium solution we brought, and it is only 6 CPS, that means it's the nano Curie we brought, okay. But still we have taken all the precautions with the wearing the gloves and other things. It is not like that we want to create something fear among of you. This is the way we have to handle the radioactivity with respect. That's what we want to show. What are the activity we brought, the entire solution bottle have only some few nano Curies. But still we are wearing the gloves and other things. That's way we are respected the activity. The Roentgen, the amount of X-ray or gamma radiation that give rise to 1 ESU of electric charge of either sign in 1 cc of dry air. The Roentgen is defined as when the radiation is interacted in 1 cc of dry air, it will create 1 electrostatic unit of charge, that is called as the Roentgen. If you convert into the energy, that is equivalent to the 87.7 x per gram. And the radiation absorbed dose, the amount of energy deposited per unit mass of the matter, the energy equivalent is like 100 x per gram is called as a Rad, and if it is a 1 joules per kilogram, that is called as a Gray. The radiation equivalent man, see what are the energy you are depositing, then we have to see that the different radiations have the different type of interaction with your matter. Then we have to consider the radiation weighing factor. All types of radiation do not produce the identical effects. The radiation weighing factor, that is the WR, has to be considered. What type of radiation is interacting with your body, that corrections has to be incorporated. For example, like X-ray or gamma radiation or electrons up to the 2 MeV energy, they will say as a weighing factor as a 1, and the neutrons, depending on the energy, it has something like weighing factors like 5, 10, 20. Then alpha particles and fission fragments, because it is having the highest LET, it is having the weighing factor of about 20. The radiation weighing absorbed dose, that is equivalent dose, is given by what is the absorbed dose and then radiation weighing factor we have to consider, that is called equivalent dose. And again, the different organs have the different function in our body, then again you have to consider the tissue weighing factor, then you will receive the effective dose. Okay, what is the energy dose you got, you multiply with what is the radiation weighing factor, and then depending on your organ, that weighing factor also again you have to apply, that is called as the effective dose. The internal exposure, the annual limit of intake is the secondary unit of internal exposure, that is called ALI, is the activity of radionuclide which taken alone would irradiate the standard man to the limit set by the occupational exposure. Means the minimum activity, suppose it has gone into your body, that energy, what are the dose we are getting, that is equivalent to the one what they set. Like any who is working on the radiation field, they have the occupational exposure about 20 millisievert. Then how much of those we are getting? This 20 millisievert could be received by the man if you anything, some amount of radioactivity element is injected by to your body. That is called ALI. The different radionuclides have the different radio half-life as well as the biological half-life. Depending on the metabolism, elimination process, at touch they will decide the ALI value. Every isotope have their own ALI values. Like plutonium is having something, or uranium is having something, or cesium, suppose you are injected, it is having different ALI values.
Sir, what does it mean by biological half-life?
The biological half-life means suppose our body mechanism also have something like that. Any external is coming, it will throw out through your urination or other ways. Then suppose you have taken something X grams, how much time it took your body mechanism throw off of your elements, X by 2. That is called biological half-life. Our body mechanism, metabolism have the tendency, anything external particles are coming to your body, that will go away. The air activity is in a working atmosphere of a radioactive laboratory, maybe inhalation route or enter, because the way we are getting this all are because of airborne activity. Suppose you are handling something powder, it may get the aerosol, and during the inhalation it may get into your body through your inhalation. Thus a working limit on the basis of Ali for the radionuclide known as the derived air concentration. Suppose depending on the Ali value, they will decide how much of maximum activity, aerosol activity can be handled in the where you are working. That is called derived air concentration. That can be done, calculated as Ali divided by, on the average about 2000 hours per annum we are working in the laboratory, and then there is called minutes, and then it is 0.02 becquerel per meter cube. From this we can calculate what is the DAC. Okay. The radiation protection, we have the one organization, the International Commission of Radiological Protection, ICRP, they will give you the guidelines. Then in India we have to follow the guidelines of Atomic Energy Regulatory Board, AERB. The radiation protection follows justification in why we are using. Suppose just like that we can't use something radio tracers, there should be some application that advantage should be more than what the damage you are getting. Then optimization, then we have to see something optimization of the parameters, in the way, suppose if you are handling something powders, the what precautions we have to use. If you are handling something solutions, what the way we can minimize this. As low as reasonably achievable, as I mentioned, maybe with the minimum time we can spend with near to the radiation, or with the minimum distance we can maintain from that, like that. As low as possible we have to always achieve. Currently we are following the guidelines of ICRP 2011, and data for those stipulations are arrived from this. The exposure for a personnel of radiation or animal or experiments, these all where they got the from this, the who are exposed to the radiation, from that they are getting this data. From the data they are decided what the radiation dose maximum we can receive. Like X-ray personnel of, yeah, this all data they are decided based on the survivors of nuclear bombs at Hiroshima and Nagasaki, and then the people who are working in the uranium mine workers and radiotherapy patient. This they are taken from the data from these all people. From that they are decided how much of those we can receive. But still that what they said there, this is very low. For the people who are working in the radioactive fields, who are employed in the some of the organizations like BRNS or anything, they can receive up to 30 millisievert per year, whereas for the common public it is only 1 millisievert. And the different organs have the different dose limits like eyes and other things that define, but still they are very much lower. If you see that, it's like a Eiffel Tower, as Dr. Daniel Babu has already mentioned here. The radiation illness only observed like a height. If you see with respect to height we are compared here, above 100 meters only you have the significant effect, and anything an acute dose over 3000 millisievert is only life threatening. Up to this point we are not certain that it will cause your death, but significantly it may give something damage. But what the dose they kept, if you compare with like Eiffel Tower height, we have something like a 1 brick for the common public, and the dose limit is only for like occupational man is like something, some of the few bricks. But you compare with height of Eiffel Tower, if you reach this much height of those, only you can have something severe effect on your, it may lead to your death, but what the dose they set on us is very, very low. This is what I want to say. So what are the minimum precautions to be taken while working in a radiochemical laboratory? They ensure that any radioactive substance which gets airborne during the handling of the open source does not enter the laboratory air. Such that suppose when you are handling something powder, we have to make sure that that should not enter your air of your laboratory, such that we can minimize the inhalation of this. They ensure that the radioactive substance does not spill on the surfaces where the radiochemical work is carried out. That's what you must have seen where we are doing operation of separation of uranium and thorium. We get something on polythene sheet, and above that only we have done. If anything spillage is there, we can clear very easily. Suppose if you have anything rough surface, the cleaning of that surface will be very difficult. That's what we kept something on polythene sheet. They ensure that the radioactive substance does not spill on the surfaces. If at all if chances are there, you make sure that that should be cleaned very easily. The surfaces should be such that in case of an inadvertent spill or radioactive material, it can readily be cleaned, easily can be cleaned. That's what we cut something polythene sheets. What are the additional features that are required as compared to chemical laboratory? If you have all the chemical laboratories, compared to that, what are the additional features we should have when you are handling anything radiochemicals? The fume hood or glow boxes should have suitable ventilation arrangements to operate at a slightly negative pressure with respect to ambience to prevent the release of radioactivity into the laboratory air. Suppose you have something like a one fume hood or glow boxes which are kept at negative pressure compared to your ambience, such that anything activity is there, it will never come out into your air, then the inhalation could be minimized. The surfaces in the fume hood or glow boxes and laboratory floor should be covered with a polythene sheet or polyvinyl chloride PVC tile to help in rapid cleanup in case of anything spillage. Suppose you are handling something liquids, it may chance spillage, you just cover with anything PVC sheets or PVC tiles such that cleaning will be easier instead of using something rough surfaces. This is a simple setup of fume hood. In your own campus also have one fume hood, somewhere in the ground floor I have seen. This is a simple setup, like one iron cabin will be there and cover with something from front glass window. They have options to put inside your hands to work and inside the fume hood. So if anyone wanted to see that fume hood, you can go to that lab. That lab is called a research lab. Then we can see this all, what that fume hood, how it will be there. The glow box, suppose if you want to handle something more powder forms which are having something significantly radiotoxicity is there, we can go for the glow boxes. It is like a containment, have one box like that, imagine like that. Then we have the glass windows, we can see that what type of operation we are doing, and we have to insert your hand, the setup will be made like gloves, gauntlets, and then we have to maintain the HEPA filter such that it cannot be go, and then it has to be maintained the negative pressure such that we have to connect to something blower systems. The containment, the criteria in handling radioactivity, why are doing the containment such that anything activity will not come to your ambient air. The contamination, the presence of radioactivity in undesired places. What is the meaning of contamination? Where it's supposed not to be there, where suppose it is there, that is called contamination. The presence of radioactivity in undesired places. It is important and essential to avoid contamination. Means maximum possible you try to avoid the contamination, that's what we are wearing all the gloves and other things. Due to its radiotoxicity, radioactivity has to be contained and therefore special features come into the picture. It has to be contained in some containers. To avoid radiation exposure by inhalation or injection, the containment has to be achieved by handling the radioactivity. Something like that inhalation, this all same thing I am repeating here. The philosophy is handle the radioactivity with respect, care, but not with fear. Therefore, one has to follow the rules and regulations while handling the radioactivity and make provisions for this while designing radioactive laboratory. We have to handle with respect and care, and then we have to follow certain rules to minimize these all effects. Okay. The classification of laboratories depending on what the level of activity can be handled, they are classified. Like you see the type C, we can handle up to 10 microcurie, that means 3.7 into 10 power 5 becquerel or less, and up to 10 millicurie we can handle, that means 3.7 into 10 power 8 becquerels can be handled up to by type B. In the case of type A, the above of this all we can handle in the type A laboratory. Now what is the criteria for the type C? That is the minimum activity can be handled in any chemical laboratory. The modifying factor is, additionally depending upon the type of operation involved, the quantities of radioactivity handled are modified by the extent of the factor shown below. Means that is a design like a total activity, but depending on what type of operation you are doing, we have to apply the modifying factor, that is storage only. Suppose the C laboratories have only 10 microcurie, if you are only for storing purpose, we can handle up 100 times of 10 microcurie, that means 1 millicurie we can handle. Then very simple are wet operations, suppose you are doing only wet operations like solutions or something like that, we can go up to 100 microcurie in the case of laboratory C type. The normal chemical operations like dissolution, precipitation or solvent extraction, the same maximum we can go for 10 microcuries. The complex chemical operations with risk of spillage, suppose you have to do something like shaking and separation, all these things, maybe we can reduce to the 0.1. The simple dry operations like planchetting or drying precipitates, we can go for 0.0, 0.1 times, means we can handle only 1 microcurie. Because when I am drying it, there is chances of aerosol formation. That's what they reduce the total, what the activity we can handle. And dry and dusty operations like, and we can go for only 0.01. That means 0.1 microcurie only. Depending on your operation, then we have to choose the what the maximum limit we can handle. At any cost, we should not cross the limit. The radiotoxicity, it is the ability of radioactive material to produce injury by virtue of its emitted ionizing radiation. The radiotoxic hazard depends on the half-life of the radionuclide. This all of you know. The half-life is are higher, that emitted radiation intensity will be lower. Maybe we can handle higher amount. And the type of emitted radiation and its energy, suppose it is emitting something alpha particles, then we have to take separate care. And if you suppose some are only gammas are there, there's different type of safety precautions can be taken. The target organ in the body, suppose it is gone inhaled, then where it is getting targeted, depending on that also radiation hazards will be decided. The rate of biological elimination from the body, some example if you see the tritium, it is only if we inhale it also, within 12 days everything will come out. And in the case of uranium, it may take around 18 days. And in the case of plutonium, it will take 80 years. That you see the rate of biological elimination from the body, based on that the radiotoxicity can be defined, and then quantities involved, how much of quantity we are handling. From this we have to consider these all factors. Some of the examples only I given here, who are having the biological half-lives as well as the half-lives of radio elements are higher, they are treated as a highly toxic. And then medium toxic, even though half-lives are more, but biological half-lives are normal half-lives are maybe less comparatively to other elements. They can treat it as a medium toxic, and then medium toxic B and low toxic. They are defined based on these all parameters. Wherever handling the high toxic, we have to take the highest precautions. The specifications for the labs, type C laboratory. The C-type laboratories mean for carrying out practical experiments recommended at university laboratories and similar research institutes. Like that, what the laboratories you have in your labs, that can be converted into C-type of laboratory. The what changes we have to do. Any chemical laboratory can be converted into type C laboratory with following provisions. A clean, well equipped chemical laboratory having one fume mode and amenability of surfaces for the easy decontamination can be converted into type C laboratory. It should have smooth floors such that if anything spillage is there, cleaning should be easy to carry out, and the walls also should be painted like what you call plaster of Paris coated, such that cleaning will be easy. And ceilings and tabletops, we should have something ceiling. In case of anything contamination is there, we can clean it very easily. The floors to be covered with PVC tiles and then washable paint for the surfaces, such that if during the washing, color should not damage. The steel or wooden workbenches and cupboards are allowed, but the top surfaces which is used for the laboratory work shall be covered with non-absorbing plastic laminates. That's what we use the polythene absorption sheets when I am using something like wood surfaces, such that if anything spillage is there, that will be very easy to clean it. With these precautions, we can handle what is the set for the type of laboratories. Each laboratory shall have the sink and wash basin, because if in case of anything after end of your operation, we have to wash our hands. There should be something, sink should be provided in the laboratory where we are handling. And then if possible, the tap we have something like elbow operation, such that the person who is already have something doubt on his hands contamination, he should not touch the tap, then further who is not handling anything should not get contamination from that. If possible, that type of operation can be incorporated, or otherwise there should be second person always, he will open the tap and you can wash your hands. Okay. The laboratory equipment. Now you see that when you are washing, suppose you are suspecting something contamination, the water you are receiving effluent will be there from your sink, that should not be used for any other drinking or any other purpose. You make sure that this effluent of your will be connected to your toilets or septic tank, we make sure that there will be no one using from that. Effluents from these laboratories can be mixed with general effluents from toilet or effluents from other laboratories, such that make sure that it will not be used further by any other applications. The storage facility, suppose you have something sources, then you have the separate storage space, maybe corner of the room should be provided in case of several isotopes are handled. Those outside the storage area at 10 centimeters should not be more than 10 microsievert per hour. You make sure that the lot of sources could not be accumulated at one corner of the lab where those may be cross this limit. Then monitoring instrument, suppose you have something suspect somewhere is got contamination, you take a swipe. By using your GM counter also you can see what is the contamination level it is have, or if at all if you want to see that what type of isotope is coming, you can go for your single channel sodium iodide detector. What the existing facilities can be converted into as a monitoring instruments in your case. In case you are handling very regularly, maybe you can approach the AERB to get the TLD. In case of any one in charge is there, you can get it. Otherwise, it may not be required for your case. The work area is compartmentalized like a zone area, white area, green area. Suppose it is not suitable for type C, when you go for any like a type A laboratory like our BRC facilities, we have the different types of areas depending on what the level we are handling. Okay. The materials handled in type C laboratory, like you see, depending on half-life like tritium, C14, phosphorus 32, these all isotopes could be handled in your type C laboratory. The rules for type C laboratory, all the work should be carried out preferably in a fume mode. The polythene sheet must be spread in the fume mode before starting any experiment to help the rapid cleanup. The eating, drinking, smoking and using snuff are prohibited in the laboratory, because when I am doing something radioactive element, I should not try to eat or drink something with the same hands. After washing and by taking proper care only we can do some other things. Then personnel should wear surgical gloves to avoid direct contact with the radioactive substance. So when you are handling something radioactive material, better to wear something surgical gloves such that we can avoid direct contact with your human body. The no work with radioactive material should be carried out by anybody having an open cut or anything skin cut, something like that, such that it should not enter our body stream. Yes. Yes. Okay, the all PPTs are available in your PC. No, we can take it at any time. Sorry? Yeah. Okay. No work with radioactive material should be carried out if anyone having anything cut, such that we can minimize the contamination of your activity into your own body streams. Okay. Suppose if anything you have to do the pipette, don't use your mouth sucking pipettes. You can use something auto pipettes what we are using in our laboratory. Any spillage of radioactive solution is there, then any accident must be reported to lab in charge. Suppose you have any spillage, you should be informed to the lab in charge, such that he will cordon off that area and he will make sure that decontamination, other things. All active material should be stored, sealed and labeled properly with the date and person's name written on it. Suppose you are doing something activity and anything is there, you have to again seal it, properly seal it such that it will not further spread, and you make a date also such that in future, suppose when they are opened, everything information will be available, such that the remedial measures can be done by your juniors. The active sample should not be removed from the laboratory without the permission of the lab in charge. It is not like that some sources are kept here and someone without knowing anyone is taken to some other places. That could be avoided. After removing the gloves, hands should be washed with a detergent solution and water. But after the end of your operations, maximum you wash your hands with detergents, such that if anything small, anything contamination is there, that could be avoided. But these all rules apply when you are handling something solutions or in some precipitates. If you are handling anything sealed sources, that already we are covered this all activity in sealed, even if you touch it also, it will not give anything contamination. But in case if you are handling anything tracers in the solutions or some other way, you have to take these all precautions. These are the dues. The get acquainted with the workplace means you should know in your workplace what is, where power supply is there, where the monitors are there. In the case of monitor means you have the GM counter, something like that. The handle activity with respect, not fear. Again I am mentioning, it's not like that with hurry something, you should not do it. Any deviation from the expected behavior to be informed. Suppose you are doing something operation, by mistake something has happened, deviated from your SOP, then it should be informed to your superiors or in charge. The wear protective equipments like gloves, lab coats and respirators. The respirators when you require, suppose you are handling something like powder sample, in normal cases you don't require, use maximum lab coats and gloves. And if you are handling continuously a very long time operation, you may require TLD. You can approach our AERB to get the TLD. And the check contamination of hand after washing. At present you don't have that facility, but you can check the where you are handling this all activity. You can swipe it and go for any GM counter. And the report cases of high count rate to the lab health physicist immediately. If any health physicist is available, if any case of any high counts are observed, you can inform to them. Follow the proper decontamination methods. If at all any spillage is there or contamination is there, you have to follow the proper decontamination methods. Follow the instructions during the usual incidents and plan drill. Use something, sometimes you can plan something drill in case of any spillage is there, how to do the react. Update your knowledge, how the decontamination procedures are everything. The loss of protective equipment should be brought to the notice of seniors or HP. In case your GM counters are there, may not be working, if you are carrying out something practicals like this, then you should be noticed to your supervisors. What are the don'ts? Don't panic or overreact during any event. Leave any used protective equipments or TLD inside the active laboratory, and don't use the handkerchiefs and water bottles or any eatable items. Wash any contaminated surface by scrubbing. You don't scrub it like anything contamination area. Work bare-handed. Don't use any time with bare hands do anything work. Don't take shortcuts other than laid procedures. Just I want to show some of the examples. He is our former director of RC and IZ, and he worked about 38 years. Sorry? Okay. Yeah, he worked in the radioactive laboratory about 38 years. Now he may be around 80 years old, and still is very active member. What I want to show that even working in 38 years in the radioactive laboratories, and he is maybe one of the man involved in our Procron 2 test also, and he definitely handled very toxic radioactive elements. Now he is 80 years old and still is very active. And that's what I want to show my former director's photograph here. And these are what I am showing that in the category type A category. These are glow box operations where some of the technical instruments will be incorporated in the glow boxes where we can handle something high radioactive elements. This is a simple setup. Now this is our laboratory where we are working inside the glow boxes, and these all people who are already superannuated. They may cost now more than 75, and still they are very active and they are enjoying their life. The person I am working here, this is almost like 15 years back the photograph. All of my seniors are retired, still they are enjoying the very peaceful life. This is what I want to say. And it's not only man, there are women power is also there. Now the girl is working inside the fume mode in our own laboratory. You can see the face, very peacefully she is working, happily also. I can see that, the girl is also with a smiling face only she is working, not with any something hurry or with fear. This is what I want to show. Okay. This is a radiation symbol. Wherever the radiation is carried out, this is a symbol. And now if you want to handle something very curious, maybe Shahir or Tapasdas are maybe handled in these hot cells. If you want to handle something in some Curie level activity, they will say hot cell. These are the facilities. The caution, finally is that if anything radioactivity you are handling, do with caution. It's not like any casually don't operate anything, but with minimum care we can do whatever radiological operations we can planning in our radioactive laboratories. So there is no problem. Thank you for your kind attention.
Any queries? You should have lots of queries because
okay.
Yes.
Good afternoon, sir.
Good afternoon, madam.
Sir, can any individual open type C laboratory in his or her own area?
Okay, there are, see, we have conducted like 109 workshops in entire India. There are some of the laboratories, still they converted their laboratory as a type C laboratory. Like you are from maybe Delhi, very
Yeah.
close to you, there is a one Pantnagar University is there. There I went earlier as a workshop. They have the type C laboratory. They are doing something radiological operation.
But can any individual whole alone owns the type C laboratory?
See,
No.
anywhere, any radioactive material handling, no, it's not by individual person. They should be institute wise. Okay, for them only we'll give the permission or supporting system and everything we'll provide it.
Okay.
For not for individual persons. It should be from organization.
Thank you, sir.
Any other questions? Okay. Thank you, sir.
Thank you.
Now I welcome V. Satyanarayan Garu for the feedback on this session.
Thank you, sir. Really, Professor P.S. Ramanjan sir, you are enlightened us regarding the radiation. We know very well that there is no space in the universe without chemicals or chemistry. But here, now I conclude that nothing will be there without the radiation. You are also observing, and also you told that in everywhere radiation is there. We are breathing air through radiation, we are eating food through radiation, we are drinking water through radiation. That means everything is linked with the radiation. And also here very important point is that every scientist and every human being should know what is the importance of the natural resources. We should not get fear due to the resources. We should help we have to get the helping nature of the resources. Suppose sir told that we should respect and care regarding the radiation, we should not fear. Also, we have the lot of the resources. Water has the resources, radiation has the resources, air has the resources. There are all the resources we have, but only you have to see the opportunities. Only you have to see the opportunities from the resources. We should not do the fear. Also, here also, he emphasized that the importance of the human power. 80 years old person is promoting the scientific intensity of the, in bark only, sir, in bark research to the other persons. That shows that how we have to be work hard regarding the research. And you are the strong persons, you are the youth, you are the pillars of our country. That's why that is the inspiration to our younger generation. Like that, sir not only explained the radiation, creation of the radiation, production of the radiation, and also different laboratories, laboratory A, B, C, and also he wanted to tell the importance of the human power. That's why everybody should encourage the research and accumulate the knowledge and enrich your knowledge, and the knowledge should pass through the ground levels of your villages and every corner of your paths. Thank you, sir. Thank you for enlightening us in such a way. Thank you.
Yeah. That was the best feedback so far. Thank you for that great feedback, sir. Now we'll have Q&A session. So students, get ready for answering the questions. After Q&A session, we will go for lunch.
Very high energetic speech. Thank you, sir. So most awaited session, right? So before that, I want to ask few things for students. Did you enjoy this IANCAS workshop? Yes. Did you gain knowledge? Yes. Okay. So for that you have to thankful to your physics department, particularly Gauri Naidu sir and ma'am, and all physics department professors. They took lots of efforts to conduct this workshop. Okay. So do you have any fear about radiation? No, sir. Very good. So do you join DAE, Department of Atomic Energy? Yes, sir. So for that, what you have to do? You have to work hard. You have to gain your basic knowledge. And finally, you have to search barc.gov.in for recruitments. So, chestara andaru? Okay, good. So, we'll proceed for our quiz, last quiz. Ready? Yes, good. So, the first question is, right, what is the annual average dose received by us through various natural things? What is the average annual dose received by us by natural things? Yes. Exactly. Correct answer. Right answer. Please come forward. 2.4 millisievert. Right answer. Tell. Mike, please. Tell you.
I'm Stella from Autonomous College, Rajahmundry, first year MSc Physics. Thank you.
The second question is, 1 curie is equal to how many becquerels? 1 curie is equal to how many becquerels?
3.7 into 10 power 10 becquerels, sir.
Right, great answer. Please tell your name.
I'm S. Vandana, Department of Nuclear Physics, Andhra University, Visakhapatnam. Every day.
No, how many?
4, sir.
Great.
You all need the highest number who got the prizes? More than 5 anyone got? So far?
More than 4.
The fifth one she is getting, na? This is the fourth one, okay.
She is very confident that she will get 4th prize also. So the next question is, biggest cyclotron in India is located at Gopal.
Dhruva, sir.
Biggest cyclotron located at
Mumbai, sir.
No, that back side here.
Kolkata, sir.
Yes, right answer. Kolkata. Please come. It's a VECC. VECC.
My name is Surya. I am from Government Autonomous College, Rajahmundry.
Okay. Next question is, to get 90% radioactivity, how much time we have to irradiate the target in nuclear reactor? Again I'll ask, to get 90% activity, how much time we have to irradiate a target in nuclear reactor?
Or how many half-lives?
How many half-lives? This girl. Yes, exactly, correct answer. 3 to 4 half-lives we have to irradiate the target in nuclear reactor to get 90% of radioactivity.
Myself, Divyasri, Nuclear Physics, Andhra University.
Next question, very easy question. Radioisotopes can be produced from. Radioisotopes can be produced from. Sir, that girl.
Low specific activity.
No. ఎక్కడి నుంచి మనం రేడియో ఐసోటోప్స్ ప్రొడక్షన్ చేస్తాము? రేడియో ఐసోటోప్స్ మనం ఎక్కడి నుంచి ప్రొడక్షన్ చేస్తాము? ఎలా ప్రిపేర్ చేస్తాము? ఏం కావాలి? నెక్స్ట్ గర్ల్ సార్.
Through charging, sir.
No. Sir, this girl. Sir, this girl. First row.
Charged by N by Z ratio, sir.
No, sir. How we can produce radioisotopes? Sir, that green color dress. Back, just.
From nuclear reactors and cyclotrons.
Yes, exactly. Nuclear reactors and cyclotrons. Tell your name and institute.
I'm Sheikh Shahida from 2nd MSc Physics. I'm studying in Government College Autonomous Rajamahendravaram.
So next question is, name of the reactor located in BRC through which majority of radioisotopes are produced. Name of the reactor in BRC through which majority of radioisotopes are produced. Reactor parent, BRC lo unna reactor peru. Yes, Dhruva reactor, right answer. What happened to boys? Okay.
Myself, Chandani, Government Autonomous College.
Okay, for boys. Next question is exclusively for boys.
BSc second year.
Okay, this question is for boys, okay? Which type of groundnut is cultivating in Andhra Pradesh? Little bit tough question, right? Which type of groundnut is cultivating in Andhra Pradesh? Okay, leave it. I'll ask another
Year
question.
47.
Okay, for faculty. Okay. TG? No, it's TG 47. Yeah, TG 47. Okay. Boys. Okay. So now we will observe exactly. So those who is raising hand first, okay? So please observe. Who was the first woman to receive Nobel Prize? Again, girls.
Curie, sir.
Marie Curie.
Marie Curie.
Okay, right answer.
My name is V. Sampurna. I am studying first MSc Physics, Government College Autonomous Rajamandri.
Next question is, radiation protection mainly done by what things? Radiation protection mainly done by what thing? Again, girls, raises first.
Time, distance, shielding.
Very good, excellent answer. Time, distance and shielding. Boys ki emaindi? Ee boys ki emaindi?
My name is Nageshwari, first year MSc Physics, Government College Autonomous Rajamandri.
Very good answer. Next question is, boys ki kaadu, girls first leputunnaru hands. Em cheddam? Okay. Which radioisotope is used for SHRI, sludge hygienization research irradiator? Okay, Gopal.
Cobalt 60, sir.
Yes, right answer, cobalt 60. Come on. Gopal also got 4th prize.
My name is Gopal Krishna. I am studying 2nd MSc Physics in Government Autonomous College, Rajamahendravaram.
Acha, next question is, what is the target material for iodine 131?
Thyroid related.
No. What is the target material for iodine 131 production? Iodine 131 production cheyadaniki
Xenon.
No. For iodine 131, what is the target material? Sir, that guy.
Sir, tellurium.
Tellurium. Okay, tellurium right answer. Tellurium 130 is the right answer. Okay, come forward.
Myself, Arun. I am from Department of Physics, Government Autonomous College, Rajahmundry.
Nice. The last question. Tell me the full form of IANCAS. This is IANCAS workshop. Tell me the full form. That girl, sir.
Indian Association of Nuclear Chemists and Elite Scientists.
Excellent answer. Right. Good. Very nice. So congratulations to all. Nice answer. Thank you so much.
So now we shall go for lunch and we'll be having valedictory start by. So welcome to the valedictory of National Workshop on Radiochemistry and Applications of Radioisotopes, organized in collaboration with DAE, BRNS, IANCAS and Government College Autonomous Rajamahendravaram. We successfully completed our 5-day workshop. We had a very informative technical sessions followed by practical sessions, and the participants really enjoyed all the sessions. Then they learned many things. We have lots of memories. So all these memories will stay us for a long time, and I hope this workshop is very beneficial for the students. And with these remarks, I would like to heartfully welcome our beloved principal sir, Dr. Ramchandra R.K. Garu, onto the dais. Now I welcome today's chief guest, Dr. Tapas Das Garu, onto the dais. And now I welcome Dr. P.S. Ramandanelu Garu, IANCAS coordinator for this workshop, onto the dais. Now I welcome Srimati C.H. Komal Lakshmi Garu, HOD Physics Department, Government College Autonomous Rajahmundry, onto the dais. And now I welcome Organizing Secretary of this workshop, Dr. B. Gaurnayadu Garu, onto the dais. Thank you, sir. So before we are going further, I would like to take feedback from the participants about this workshop. So now I call upon Dr. J. Suresh Garu for his feedback.
eminent distinguished members on the dais, our honorable and respected principal of this one of the prestigious college in the state of Andhra Pradesh in general, and the first NAC A+ college in the entire country in the government sector, a good academician, researcher, administrator, and a NAC peer committee member who always strives hard to make this institution from the state level to the global level, our beloved principal Dr. Ramchandra R.K. Garu. And today's chief guest, so he has given an informative knowledge about the radio analytical techniques and isotopes, their widening importance in various aspects of our life, our beloved chief guest. IANCAS, the coordinator, Ramanjul Garu, the program coordinator and head of the Department of Physics, Srimati Dr. Komalakshmi Garu, and the organizing secretary, the young and dynamic, who has made a strive hard to make these 5 days programs to be a remarkable in the history of the Department of Physics of this oldest department. Our beloved friend, my friend, Dr. Gauri Naidu, and all the scientific officers, from the BARC Mumbai, my fellow participants, and to all the teaching physicist fraternity of the Government College Rajahmundry, and all my dear students, a very good afternoon to one and all. I feel it's a deep privilege to be a part of this wonderful program, to be associated with these 5 days, a national workshop organized jointly by the BARC Mumbai in association with Indian Association of Nuclear Chemists and Allied Scientists, in collaboration with our parent institution, Government College Rajahmundry. Really it's an heartsome and really it's a mind-blowing. Earlier there was a misconception. Actually, I am a student of Venkateshwara University. We have a branch of radiochemistry. While I am a student in 1997 at SV University Tirupati, we are having environmental chemistry and radiochemistry. But very few of the people who used to have the last priority during our admission, those who choose to be a part of these radiochemistry students. There was a lot of conception that only organic and analytical people will have a widening opportunities and avenues in every part of our human life. But as on days comes across, now it has realized into reality, or it comes into a limelight, that what part of the nuclear energy, what part of this atomic energy will have a broader perspective, apart from this IT field, apart from this artificial intelligence, apart from this machine learning, whatever it may be, the physicist in every walks of life, associated with the technological upgradation. But it has come to reality, these 5-day sessions, what type of an extensive research work that's going on in India about the impact of this atomic energy. And I am very proud and it's a very great opportunity to all the young scientists, young researchers, in and around from the entire part of the India, that we are much well thankful to the BARC scientists. So we have given a lot of widening chances to know about what type of research that is going on by the Department of Atomic Energy, related with the peaceful uses, opportunities, technology for society development, and the impact of radioisotopes applications and the analytical techniques in a wide broadening branch. Really, on behalf of the entire participants, so we extend our heartfelt thanks to the BARC scientists and all the scientific officers. So we have given a widening chance to all of us to know the more opportunities, more avenues, more scientific research, more scientific temperament that has to be incultivated by all the young scientists in India, especially the nuclear physicists, the nuclear chemists, and all the allied scientist people. So there will be a lot of chances that came into existence only with the exposure of these great eminent people. So on behalf of the entire participant fraternity, so we extend our sincere thanks to all the scientific officers, the resource persons, especially those who came from BARC Mumbai, for spending their valuable time with us in these wonderful institutions, and hosting this 109th IANCAS National Workshop in our Government College Rajahmundry. Really, it's a great honor and pride to all of us. So on behalf of the entire faculty, so give him a good claps to all the BARC scientists, to all the scientific officers for hosting this wonderful event in this college, to say something about this Department of Physics. So really, on behalf of the participant, we congratulate all the faculty members, both the teaching and non-teaching staff members. So we have spent a lot of, their sleepless nights to make this project, to make this subject into a limelight for these 5 days with an extraordinary skills and their commitment and their wonderful cooperation. So on behalf of the participants, I congratulate the entire physics faculty of our college for hosting a wonderful event. The hospitality, the food committee, and whatever the sessions, really from the morning to afternoon, we had a forenoon sessions of the resource persons, and the evening, so we had a good hand-on experience on the applications of the radioisotopes, especially the Geiger-Müller counter, or scintillation counter, and whatnot, everything, really once again. So with the last but not the least, I remember the beautiful quotation quoted by the Sanskrit sloka that is about the Brihatala Upanishad, that asatoma sadgamaya tamasoma jyotirgamaya mrityoma amrutangamaya loka samasta sukhina bhavantu. I pray to the Almighty that I must be overcome with ignorance to from untruth to truth, from knowledge to wisdom, and from mortal to immortal. So definitely this nuclear energy, this atomic energy will give a wave for the entire world, that this type of energy will try to give a lot of impact in due course of time, and our country will be at the top positions on the Vikisit Bharat to be a developed nation with applications of this atomic energy and nuclear energy. So with these few words, I extend my hearty thanks to the entire organizing team for giving an opportunity to say something about this wonderful event. Thank you one and all, and thank you very much.
Thank you, sir, for your very elaborate feedback. Now I welcome our Vice Principal, Sir Dr. Murthy Garu, onto the dais. Sir, please. Now I call Simrat Kaur Nanda from Delhi University for her feedback.
Good afternoon to one and all. Good afternoon, Principal Sir. Good afternoon, sir. Good afternoon, ma'am. Good afternoon, scientists, sir. Actually, when I was in Delhi, I never thought that I will get an opportunity to visit this workshop itself. I feel much more privileged than anybody else because I get hands-on experiment. I get much more knowledge and much more insightful session to become a nuclear scientist for India, and I will be very privileged if I pursue this passion. Thank you so much, sir, and one more gratitude I gave to God and my friends over there who didn't treat me like that I am from Delhi. And from past 5 days, I realized that language is not a barrier. Thank you so much.
Thank you. Thank you for your feedback. A bit emotional, but great. Now I welcome P. Kavya from Adikavi Nanya University for her feedback.
A very good afternoon to the respected scientists and the organizers. I am P. Kavya Tanushree Reddy from Adikavananaya University, Rajahmundry, Department of Physics. From the very first session to the last hands-on experiment, this entire workshop has been nothing short of extraordinary. The depth of knowledge, the depth of theoretical concepts, the clarity in explanation, and the real-world applications of radiochemistry has been left us truly inspired. This experience will stay with us as a guiding light in our scientific journey. Thank you for the time, patience, and the wealth of knowledge you have shared. We look forward for more opportunities to learn from you in the future, sir. Thank you so much.
Thank you, Kavya, for your feedback. Now I welcome S. Vandana from Andhra University Nuclear Physics Department for her feedback.
Good afternoon to everyone, scientists over here and all the dignitaries on the stage, lecturers and my co-participants. I am S. Vandana, Department of Nuclear Physics, Andhra University, Visakhapatnam. I think the success of this workshop lies in interactive nature between scientists and participants. I feel this is more interactive than any other workshop, and we also felt very close to ask our doubts to them, and they also explained it very clear. I thank all the organizers and scientists for giving me this opportunity. On behalf of all the students from Andhra University, thank you very much, sir.
Thank you, Vandana. Though I wanted to take feedback from all the participants, due to the time constraints, so I'm stopping here, and let us go to the next part of our valedictory. Okay, maybe I can take one more. Anyone, just one, last one, please.
Okay. Respected Principal Sir, Government College Autonomous Rajahmundry, and respected dignitaries on the dais, and respected Vice Principal Sir and HOD of the Physics Department, and all the participants, my dear friends and my dear students, good afternoon to one and all. Actually, this workshop, 5-day workshop, has excited and given highly energetic to our students and participants, and also it is highly enriched and enthusiastic, and also enlightened the minds of all the participants because of the overall explanation and in-depth of the analysis and also hands-on experience. Till now, we have observed a lot of things, but due to this workshop, we learned a lot of things which are relevant to our studies. We know very well regarding the importance of radiochemistry and radiation, but today we are observing a lot of diseases, especially the cancer. This is the cancer penetrating to the every corner of the villages. Only one source, the cancer, it is removed through the only due to two things, whether the medication and radiation. But medication, we are unable to stop this disease, but only the option is radiation. The radiation comes only due to these isotopes. This is very important. It is not only for the national workshop, it is highly useful for the international, throughout the international. Because not only in India, in every country, they are facing due to this cancer type of the diseases. That's why it is a high time to focus this kind of the radiochemistry and the applications of the radiochemistry. This is not enough to penetrate the knowledge of this regarding the radiation. We have to develop a lot of instruments and a lot of detectors and also a lot of applications due to this radiation. That's why here we humbly request you to our principal sir, we conduct more this kind of the workshops to generate and also to penetrate this kind of the knowledge to the normalized peoples also. Thank you, sir. Thank you so much for giving this kind of opportunity.
Thank you, Satyanarayan Garu, for your feedback. Now, I would like to welcome.
We also require something constructive suggestions. All the people are praising. If anyone wanted to give any suggestions, come forward and give anything suggestions. Where we are lacking, we should know it. That's what I want to say. If anyone wanted to give anything constructive comment, please
Yes, please.
forward. Where we have to improve that, first you have to highlight.
Respected dignitaries on the dais and half the dais, a very good afternoon to everybody. Today we are celebrating a wonderful afternoon. This workshop can create awareness about the work, research work carried out at Baba Atomic Research Center and Department of Atomic Energy. This type of programs are very useful for creating awareness about the research programs conducted at national level important research institutions. Because people always think BARC means they are working on atom bombs or purifying the radioactive materials. But there is a lot of work, research work carried out at BARC or Department of Atomic Energy or DRDO, which is useful for common man. So, but people don't understand that. With this type of programs, this awareness will be created in the educated people. So, from this 5 days of workshop, we will learn what is the peaceful applications of nuclear energy. What are the career objectives for students at BARC, etc. Next, we can know the radiation will also useful to store food materials. Radiation energy is useful to store food materials. That is acting as a preservative. So, radiation is a food preservative. There is a very good attitude. Next, we are using radioactive isotopes to treat cancer. Next, this type of approach is very important to treat cancer and etc. for development of the brain. Next, now people are afraid about radioactive isotopes, but for every research field we have some problems. With precautions and further taking care, we can overcome the problems. Even chemistry also, in the lab, we are using cyanide. Cyanide is very dangerous. In the same way, in chemistry lab, we can work with nerve gas. Nerve gas means that we don't have any smell. That will accumulate into the nerves and all the nerves will be deactivated. Finally, the chemist will lose his control on body. That is the nerve gas. Even we are working with nerve gas also. But in the morning they said we can use fume hood for that type of reactions. In chemistry also we are doing that type of reactions in the fume cupboard. So, for every field we have some problems, some advantages and some disadvantages. So, with proper care we can overcome that problems. So, because I am saying here a lot of students are there. So, all the students will note this point and create a positive attitude. Sir said morning, don't fear, only respect, care. That will overcome all the problems in the lab. No fear, only care and respect. That is the important. So, next, the program is well organized and time maintenance arrangements are very good. So, the speakers will provide very valuable information in a useful manner and understandable. So, I am thankful all the speakers and college authorities to organizing the event in a successful way. Thank you all of you.
Thank you, sir. Yeah. So, one more chance. Actually, the people from BARC wanted to know, is there any improvement to be required during these workshops? So, they want suggestions, not only pricing. They want suggestions, because we have lots of faculty members here.
So, Honorable Dyers, teacher friends, I have only one suggestion, sir. Actually, we learn these techniques because we are from the science background and we can easily understand what you teach to us. Actually, I have only one suggestion. Whenever you organize such type of the workshop, please organize one popular lecture in local language for the general people. so that they will also come to know about this radio science and this technology. Okay, thank you very much.
That's a great suggestion actually, yes.
Shall I respond?
Yeah, you can respond.
Yeah. See, we are conducting these national workshops through IANCAS. The IANCAS will select the resource team. Whenever they are conducting this workshop in the state, they will select the resource persons, at least 1 or 2 people from the same language. That's what I am selected as a coordinator. Of course, the presentation could be given in Telugu, but frankly speaking, some of the technical terms to pronounce in Telugu is very, very difficult. Okay, I have to accept that, first of all. And second thing, during our practical sessions, the maximum we have spoken in only in Telugu language. But in some of the technical terms where we are presenting, that all Telugu words, we also don't know, frankly speaking. Okay. So once again, for that also, yeah, once again, earlier, wherever we are conducting this type of national workshops, we used to go different schools to give at least one lecture and then to demonstrate something practicals. But now the schedule is so tight, and the BRC authorities also have something limitation to send to maximum number of resource persons. We could not go anywhere. That I accepted that. But at least 1 or 2 school workshops is being conducted. But this time we could not do it because of we are limited manpower or resource persons in our workshop. That's what we could not do it. But thank you for your suggestion. This the same thing I will inform to our IANCAS authorities. Thank you.
Thank you, sir. Now, I welcome Dr. Tapas Das Garu, today's chief guest, for his remarks.
Yeah, Dr. Ramakrishna Garu, Principal, Government College Autonomous Rajamundry, Dr. Murthy, Vice Principal, Madam Kamala Lakshmi, Head of the Department of the Physics Department, Dr. Gauri Naidu, Faculty Department of Physics, my colleague and the coordinator of this workshop, Dr. Ramanjanalu, the faculty members of this great institute, dear participants who have assembled not only from this college, not only from Andhra Pradesh, but from the other states also, my dear colleagues from BRC, ladies and gentlemen, a very good afternoon and namaskar to all of you. So it's an honor and privilege for me to stand before you as we conclude the 109th edition of the IANCAS workshop. This one-week journey has been filled with learning and invaluable insights into the fascinating world of nuclear and radiochemistry. The road we have traveled together has been paved with knowledge, curiosity, and shared desire to explore how these sciences contribute to the betterment of the society. The field of nuclear science came into existence towards the end of the 19th century, when many discoveries were made in a short span of time. These include the discovery of X-ray by Roentgen in the year 1895, then the discovery of the radioactivity in the very next year by Professor Henry Becquerel in 1896, and the discovery of the electron by Professor J.J. Thomson, again next year, that is in 1897. But the real growth in this field started when first the artificial radioactivity was discovered, and with the production of phosphorus-32 in the year 1934. Since then, many such radioactive substances have been produced and utilized for the benefit of the society, and their applications have spanned many fields such as research, healthcare, industry, food and agriculture, as you have seen from some of the lectures. Department of Atomic Energy, since its inception, is at the forefront in bringing the benefits of the radiation and radioisotopes in the day-to-day life of our countrymen. Indian Association of Nuclear Chemists and Allied Scientists, which is popularly known as IANCAS, was founded in the year 1981 by a group of senior academicians and radiochemists in India. The major objective of IANCAS was to popularize the subject of nuclear and radiochemistry among the academic community and the use of radioisotopes and radiation sources in education, research, agriculture, medicine, and industry. The target group initially comprised only the faculties of the Indian universities, but later we have expanded it to research scholars, postgraduate students, and even school children up to the secondary level. The objectives of this association is fulfilled by 4 different ways. That is organization of the national workshop, and this is the 109th of that series. Publication of the thematic bulletin and books. So you can visit our website www.iancas.org, and you will see many thematic bulletins which are freely downloadable, and you can see whatever we have presented here in last few days, everything in much details is available in the website. Institution of the awards, as well as information exchange through this website. Since its inception, IANCAS has registered a continuous growth in the number of live members, and today we are happy to say that we have more than 2,400 live members and some corporate members, and that spreads over a wide spectrum over national and international institutes. I take this opportunity to request you, particularly the faculty members as well as research scholars, even the students, to join us in this endeavor to spread the nuclear science, technologies, and application of the radioisotope to the countrymen. So if you are interested, if you like our workshop, I'll request you to kindly join us as a member of our IANCAS. The forms are available in the website www.iancas.org. So today this association has become a forum for pursuing and propagating nuclear sciences and endeavors to motivate scientists to achieve excellence in the field of nuclear and allied sciences. The association has instituted a number of awards to encourage young researchers and scientists for pursuing activities in the field of radiochemistry and application of radioisotopes. The detail can be available from the website. Throughout this week, we had the opportunity to attend 13 enriching lectures, with the highlight being the keynote address delivered by Dr. Prashant Kumar Mahapatra, former Director, Radiochemistry and Isotope Group of Bhabha Atomic Research Center and present President of IANCAS. His words not only provided a deep understanding of the field, but also inspired us to consider how we as professionals and enthusiasts of this domain can contribute to the society. We have learned about fundamental principles that govern the nuclear and radiochemistry, and we have gained a comprehensive knowledge and understanding of how radioisotopes are being utilized for a wide range of societal benefits, from medical applications to industrial troubleshootings to the food preservation and beyond. But beyond the lectures, the hands-on practical sessions and demonstration were just as valuable. These interactive experiences provided you the opportunity to bring theory into practice, offering a deeper understanding to the subject matter. I trust that each of you now has a richer appreciation of the practical side of nuclear and radiochemistry, and that you can take these lessons forward in your work, research, and professional lives. As we reach to the end of this excellent workshop, I hope that each of you leaves with a renewed sense of purpose and inspiration. The journey does not end here. In fact, it's only just beginning. Armed with the knowledge, skills, and experiences gained over the past week, I encourage you all to continue exploring, innovating, and pushing the boundaries of what is possible in this field. In addition, I hope the connections and friendships you have forged during this workshop will continue to flourish. Networking and collaboration are integral parts of professional growth, and I trust you will continue to learn from and support one another long after today. Before we close, I would like to express my heartfelt gratitude to all the speakers, resource persons, organizers who have worked tirelessly to make this work a success. To all the participants, thank you for your active participation and enthusiasm. You are the reason this event is so impactful and meaningful. Let us live here today not just as participants of a workshop, but also as ambassadors of knowledge, ready to apply what we have learned in the service of the society. So with this few words, I thank you again, and Jai Hind. Now I want to bring it to your notice that IANCAS will be organizing a symposium called New Car. It is a very old series and one of the, I think, oldest and one of the biggest conference in nuclear and radiochemistry during April 23 to 26 at the DAE Convention Center, Anushakti Nagar, Mumbai. So I'll request the faculty members, students who are working in this field to kindly join us. The last date of submission of the abstract is February 15th. So there are still few days left, and I'll be happy to see some of you in Mumbai. Now, on behalf of IANCAS, we would like to donate one radiation detector, GM counter, to the department. And I will urge the faculties, principals, sir, and the staff members as well as students to kindly use this instrument. Otherwise, in some places we have seen that instrument has been donated, but it is not being used and it has gone bad. So we will be happy if it is continuously used for the practical, and if there is any problem, you can contact us. I think Dr. Ramanjanuli can be contacted. He is the coordinator. So we will try our best to solve that issues. But IANCAS will be happy if it is used for the dissemination of the knowledge as we have done during the practicals.
The instrument is already given in the lab. Formally, we are giving a certificate. I request principal sir, please accept.
Thank you, sir. Thank you for the instrument and also the radioisotope. We promise you that we will be using it very extensively, and we will be in contact with you for the updates about the instruments usage. Now we will have certificate distribution. Yeah, I'll read out the names. Please come fast. Pradeep TL, Indian Institute of Technology, Bangalore. Indian Institute of Science, Bangalore. Rajiv S. Vatkar, Department of Physics, Shivaji University, Kolhapur. Vijay Anil Dai, Department of Physics, V.V. Giri College, Dumpagadda.
PVN Acharyulu, lecturer in chemistry, Government Degree College, Tekkali. Okay. Sumalata K, Department of Physics, SVD Government Degree College, Nedavalu. Sri Satyanarayana Murthy, SRVBSJ, Maharani College, Peddapuram. Dr. Nageshwar B, Department of Physics, V.S. Krishna Government Degree College, Visakhapatnam. S. Narayana, Mr. S. Narayana Vavelapalli, Department of Chemistry, GDC, Vijayanagaram. G. Jeevana Monica, Department of Physics, Government Degree College, Chintalapudi. Srimati. Mr. C.H. V.B. Vasant, Department of Physics, B.V. Raju College, Autonomous, Bhimavaram. Mr. K. Surya Venkata Srinivas, Department of Physics, Government Model Degree College. Simrat Kaur Nanda, first MSc, PTJL Nehru Government College, New Delhi. So now I call as a group wise. Second MSc Physics students all, Government College Autonomous Rajahmundry, please come. All second MSc students, 7 members. Gopal, Gopal, take this and distribute.
All second MSc students of MSc Physics, Rajahmundry.
Gopal, no distribute. And next, all first MSc Physics students, Government College Autonomous Rajahmundry.
Be ready.
Be ready and come to back side. Come here in this way. Come. Sir. Lawrence, sir. You come back. Chala. अरे मेरा अंदर फर्स्ट ईयर है क्या? Next, be ready. Second MSc Physics, AKNU campus, Tadepalligudem. All 4 members, please come. Sir, may distribute change. And next, be ready. Adikavan Annaya University, Rajahmundry. 3 members. Come. Sir, you come. Next, be ready. First MSc Nuclear Physics, Andhra University. Please come, all the members. Come first. Certificate. Now ready, second BSc Physics Honors, Government College Autonomous, Rajahmundry. Second MSc Nuclear Physics, Andhra University, please come. మాది మిస్ అయిందంటే ఊరుకోండి అన్నీ రాస్తాం. కూర్చుని పోండి కిందికి లేదండి.
కొంతమందికి ఎందుకు వెళ్ళండి వీళ్ళకి అర్థం లేకపోతే
చాలా ఇంకా క్రౌడ్ అయిపోతుంది.
వీళ్ళు పంపించేసి
వీళ్ళు వెళ్ళిపోయిన తర్వాత అక్కడే నుంచి ఇప్పించేసి
అక్కడ ఇప్పిద్దామా సార్? ఇది ఫ్యాకల్టీ అందరూ ఇప్పుడు మా కాలేజ్ ఫ్యాకల్టీ
వాళ్ళు ఇక్కడ వస్తారు కదా.
వస్తారు సార్. పిలిచేస్తే నేను పిలిచేస్తారా?
మీరు పిలవండి.
డాక్టర్ ఇవి డాక్టర్ అది టిక్ పెట్టలేదు అందరూ
ప్రిన్సిపల్ గారు ఇప్పించుకోవాలనుకుంటారు
సార్.
అయిపోతుంది.
From Government College Autonomous Rajahmundry, Department of Geology, Srimati M. Vijay Santi, ma'am. Sri Kota Ganiraj Garu, Sri N. Nageshwar Rao, Department of Botany. Dr. D. Sailaja ma'am, Department of Geology. Dr. Sri Raviteja Ji, Department of Geology. Dr. N. Baby Nirmala, Department of Chemistry. Dr. L. Rajeshwari, Department of Chemistry. Dr. J. Suresh, Department of Chemistry. Baby Nirmala. Sorry,
ఇదేనా?
sorry. Last but not least, I welcome all Department of Physics, Government College Autonomous Rajahmundry. Srimati C.H. Kamal Lakshmi, Dr. Yesu Basha Sheikh, and myself. Dr. D. Sanjeev Kumar. Subhash Durga Rao Sarda. వెళ్ళండి అందరూ ఒకసారి గ్రూప్ ఫోటో తీసుకోవచ్చు.
చివరిలో తీయొచ్చులే, ముందు ఒక్కొక్కరు తీయనివ్వండి. తీసుకున్నారా? ఒక్కొక్కరు తీసుకున్నా
ఎక్కడ అలా ఈ మధ్య ఇక్కడ వరకు కవర్ అవుతుందా మూర్తి గారు? మరి అది మీ కెమెరా అలా ఉండాలి. భాష సార్ అది వెళ్దాం. మరి మీరు వచ్చినాక చూడండి, అందరూ మీకే క్లాస్ కొడుతున్నారు వాళ్ళు. సార్ ఇండివిజువల్గా కూడా తీసుకోలేదు, ఇండివిజువల్గా తీసుకుందాము.
ఏ వాళ్ళ డిపార్ట్మెంట్కి ఇచ్చేస్తారా? సార్ వస్తారు. ఏం మేడం వస్తారంట ఫోటో?
డిపార్ట్మెంట్ ఆఫ్ జియాలజీ దుర్గారావు సార్.
ఫీడ్బ్యాక్స్ కోసం వెళ్ళాను నేను. అసలు ఎవరు చదవాలా, డిపార్ట్మెంట్ అందరూ వచ్చేసి మీరు తీసుకున్నారా మేడం?
ఎవరికి మనం పదండి, మనం ఫోటో మామూలు సార్ చెప్పండి సార్.
మీరు Thank you. Now we will move on to the next part of our valedictory. Now I please settle fast. Yeah. Now I welcome our beloved principal sir, Dr. Ramchandra Arka Garu, for his remarks on this workshop. Sir, please.
So very good evening to you all. On stage, one of our chief guests today's valedictory function, Dr. Tapas Das, Head Radio Pharmaceutical Division, Baba Atomic Research Center, Mumbai, and Dr. Ramanjanel Garu is coordinator and convener, I guess it is IANCAS, and my vice principal, Dr. Shiramurthy Garu, and Dr. Komal Lakshmi Madam Garu from head of the Department of Physics, and Dr. Gauri Naidu, he is organizing secretary of this 5-day national workshop, and different scientists from BARC, and HODs and coordinators and participants across the country, press and electronic media. Once again, best wishes on the valedictory occasion on this 5-day national workshop on radiochemistry and applications of radioisotopes. So it's really very happy to host this wonderful workshop for the last 4 days, and this is final day. After COVID, many workshops or many seminars, national and international, being conducted hybrid mode. Most of the time, all the participants had habituated to participate through online. So really offline is very limited, and interested candidates only can get the opportunity to participate. But we planned it in a meticulous way, and from the beginning, Dr. Gauri Naidu has initiated the process, and we had a lot of conversation mails, IANCAS to Government College Autonomous Rajahmundry, and finally we have got resounding success in executing a 5-day national workshop on radioisotopes. As we know all, for the last 4 days, all the students have seen them in an excited mode. So, because of the radiation which they imbibed inside, and they are all excited. And for the last 5 days, they participated well, and they learned a lot about the fascinating experiments in relating with the radioisotopes. So as we know, a number of numerous applications are there on the radioisotopes, medicine especially, and scientific research and industry. So as we know that after discovery of radioactivity, Madam Curie saying that, so life is not just a matter in faith. So life is a matter of physics and chemistry. So after discovery of radioactivity. So after discovery of radioactivity, really in 1869, so it has given a big boom for physics and chemistry people, and lot of experiments have been planned, and lot of societal benefits are have been existed. So really it gives a lot of knowledge for our students, and also the Department of Physics had its own identity in the college actually. So in the beginning, I guess 1930, the department was established in the college, and thereafter 1973, PG Physics started with 6 numbers, and 2009 research programs has been introduced in the department. So like that, the department had a journey, and the department has very good name and fame across the globe, I can say it is, because I am a physicist. I worked in the department as a lecturer and worked as a HOD, and now principal of this prestigious institution. So this is all because of the department. I worked the department for the last 18 years, and then we have conducted many programs and innovative programs. We conducted program with IISc Bangalore, one 15 days refresher course. Like that, some innovative programs we have organized, and with this department, the highest beneficiary of the department as a faculty is me only. So with the working with the department, I got an opportunity as a Roman to receive as a Roman postdoc fellow from the department. So after completion of my PhD, after 15 years of my PhD completion, I got an opportunity to work as a postdoctoral fellow in USA. So that opportunity has given to me by the department. So it is, I have emotional connection is there with the department. Whatever the department execute the program, definitely we have some, a remarkable part is there with the department. So that's a great thing. And for the last 5 days, I observed the workshop has planned very meticulously, time to time, morning in this hall, excellent theoretical lectures, and not only just related to subject and a number of application part. And sir especially has given wonderful lecture on radioisotopes for human beings, and then how the pharmaceutical industry works with the radioisotopes and all. Not only sir and all other scientists who came from the BAC given their exciting lectures. We all benefited from your excellent talks, definitely. And also, one participant pointed out a popular lecture. So definitely that has to be planned by the Department of Physics. And if we would have known this before, definitely we will plan this particular radioisotope concepts and radioactivity on these kind of things in in public, and as well as most of the educated persons also, they have their own negative ideas or impacts are there. So because whenever if you talk about, if you discuss about the radioactivity, we are always seeing the negative side only. So whenever we talk about the radioactivity, Hiroshima and Nagasaki, to stop the Second World War, lakhs of people were dead, and the radiation still escalating there in the Hiroshima and Nagasaki. This kind of one-sidedness is there in the people's mind, but we need to remove that. So there are a lot of faithful applications are there, nuclear energy and radioisotopes in medicine, scientific research, industry, and number of applications are there. So that also we have to take into the public and as well as the school children. So actually, initially we had one international conference with University of Lowell. At that time we have popular talk with the scientists. at Anam Kala Kendram. Nearly 800 school children in and around Rajahmundry we gathered, and we have given wonderful, and we organized wonderful lectures on renewable energy resources actually. So this kind of nearly 5 to 7 members are there from the BARC, and then meeting with the scientists. If you put a tagline and if you organize it, that is also very good, impactful program, because anyway all the way you came here and you organized well this workshop, but we can take this kind of message to the public as well as school children also, that they can also motivate to divert their mind towards the science and applications and its applications. So anyway, my heartfelt thanks for all the participants who made a resounding success for this workshop, especially the Department of Physics. The people, they work meticulously, and their planning and execution really awesome. And just now, Ramanjanil sir told to me, they treated as, they used to go to a very maryada, honoring. That's so outstanding. So, and each and everyone whom I interacted, then everyone says, your hospitality is superb, and you're receiving, and in almost all the dimensions, what you are treating is definitely, we have overwhelmed. That kind of response we received from the scientists as well as the participants. That entire credit goes to the department and organizers, especially Kamalakshmi Madam and other colleagues and Naidu. Really, it's a good program, and in future also we would like to conduct this kind of workshops, because hands-on experience definitely leave its own mark on learning. So definitely we'd like to opt this kind of workshop in future too. So once again, thank you all for a wonderful workshop. Thank you.
Thank you, sir, for your valuable words. Now I welcome Srimati C.H. Kamalakshmi Garu, Head of the Department of Physics, for her remarks on this workshop.
Good afternoon, everyone. Respected Principal, Dr. Ramchandra R.K., and the Vice Principal, Dr. Sriram Murthy Garu, and the Chief Guest of this today's occasion, Dr. Tapas Das Garu, and the convener from IANCAS, Dr. P.S. Ramanjanil Garu, and all the scientific officers who has come from IANCAS, BARC, and my dear colleagues, teaching and non-teaching staff, dear participants, and my dear students, a warm welcome to this validatory function of 5-day national workshop on radiochemistry and application of radioisotopes. So firstly, when we thought of organizing this workshop, when we discussed with our principal sir immediately accept this. So I am very thankful for the principal sir for encouraging us to organize this workshop. Next, when we decided to conduct this workshop, it has been taken long ago, that is in the month of, I think, July, and we have implemented this plan, frankly speaking, only 10 days before the starting of workshop. So only because we had the vacation, so after vacation we had only 10 days, and this implementation organization of workshop has done only within 1 week. So frankly speaking, the collective work of our physics team has taken this. And also I am proudly says that only we have planned in the morning session, that is 7 days, and afternoon session we used to take the classes. Morning session every day we used to meet for half an hour, what are the plans to be executed and what are the works to be given to the different committees, and what the works has been executed. Only from 27th we have started, and the work has been, and we have implemented everything from 27th to 2nd February, and on 2nd February evening 8 o'clock we have completed the work. So this is only the collective work done by our physics department, teaching and non-teaching staff. And apart from this, the supporting staff, that is for decoration, Murthy Garu, and for audio visual and the computer work, Praveen Garu, and other supporting staff for other works has been for donated for keeping the seminar hall clean. So all has given a timely work. So this is why this program has gone very well. I am very glad to say this is a collective work, not a single work of the department. And if you go for the resource persons, from the lecture starting from the first resource person, that is PK Mahopatra sir, to the ND session of the Ramanjanil sir. So all the resource persons, Dr. P.S. Ramanjanil garu and Sabji Patro garu and Atunja, Dr. Atunja and Shahir Alim Khan and Chandrasekhar sir. So everyone's lecture is very valuable, and also the insights they have given is very informative. And one thing I want to say is their cooperation, friendliness, punctuality has given a fragrance to this workshop. So we thought that this work has not gone well. So they are very modest, and their simplicity and friendliness has led in this work to an extent of great excellence. So I am very thankful to all the resource person who has come here and have given a good experience and also very memories to our students and also the department. Going to the participants, we thought these participants and their interaction, this workshop has not gone well. So I have seen each and every participant has been involved in doing practicals, and also they are keenly listening each and every session, because what the quiz they are going to ask, I have to win the prize. That is their motto. So I have seen, once I have observed, so I have to show that if any students, they don't tell anything, we are going to give the answer, but they have not given any chance. So
I requested them, if it is possible, sir, please conduct, give me permission as soon as possible to conduct our college. Then, okay, but it is very difficult to conduct in the year of 2024. Then they said, I think Dr. Sandeep Kumar Sharma sir told that. So mostly in the year of 2025, or it may be February, March, we will be getting back to you through mail. Then I said, okay. So at least I got a positive response from them. Then I think exactly from now, it is exactly 3 months back, I received a mail from Secretary IANCAS. Our proposal has been received, and if it is okay, so we will, if you are okay in the month of February, March, then we will go to conduct the IANCAS. Then there is a lot of conversations. There is general formalities from the college, like they asked the letter from the head of the institutions. So then the same day that I have given the reply to the IANCAS secretary, then they said okay, and then they have given our most dedicated and beloved our IANCAS convener, Dr. P.S. Ramanjanil garu, as IANCAS from the BRC side, IANCAS side. So then this has begun, I think, around 2 months back, and then we have started. I have started preparation of brochure, and then sir has given certain kind of inputs, and then I've started to implementing. Again, I sent back, sir made some kind of certain corrections, and then finally we make it into a practice. And then we have, from our college side, we have released the flyer and circulated. So this is the way that we have started this. The initiations of conducting this 5 days 109th DA BRNS IANCAS National Workshop on radiochemistry and applications of radioisotopes. So actually there are two things here. One, to bring the permission to conduct it, that is the one way that I have done from my side, because I am very fascinated to as far as my subject is concerned. That is one thing. Second is thing when sometimes we get the permission to conducting this with a huge number of participants, around 100, it is not easy. So that there are several factors. It may be accommodation, it may be food, it may be making the arrangements for the conducting the workshop. It is not so easy. So then this is because of that our college, our department faculty, unity and the dedication and their interest making this is possible. So I am very much thankful to our principal sir. Whenever I taken a printout as we got the permission from IANCAS, sir, we are going to conduct this workshop. Then sir said, okay, so you go ahead. Whatever support that I can give, that I will give the support that you people that just go ahead, that I can do whatever the things that I can do. Then so like that also, then we started permission from the principal sir, and then with all the corrective efforts of the Department of Physics, right from, as madam told, that every day just we started the 10 days before the commencement of this workshop for the arrangements. But this is all the things behind that I have done. So then we have done a lot of committees like food and bags and identity cards and flexes and other things like there are our G. Srinivasa sir and Ramu sir, they have done the team, whole team and Lakshman sir and then the whole team, they have done a wonderful arrangements for making all these identity card bags and flexes, everything, whatever. Then a lot of corrections and then they have gone, sit for around at night, 8 o'clock, 9 o'clock and then come up with the corrections and then they send again. There are a lot of work we have done, very, very short period. And then also this registration committee and refreshments, the ladies team, Durga Lakshmi madam and then Bhargavi madam and then Padmavati madam and then our students and then also our another team is called accommodation and all the things, our Harinath Reddy sir and then Babu sir and then Basa sir for his insightful inputs and KVS sir and me has gone to a lot of places for sponsorships and along with other faculties and then also our senior sir, we call him as a senior because his name is Niranjan sir, is our food coordinator. So please give a big claps to him that actually sir is coming every day from the Vijayawada. So when it is completed, he go into the bed train, is talking to phone, sir, next day we are planning to make this kind of food menu. Are you okay or not? Like he's always talking with the madam. So he's okay, then we will go with the order, then we will come back like that. So like that, all the faculty members and Rajsekhar sir and Srinivas sir is anything like it may be like certificates or maybe anything. If you want from our side, then they're ready to do the things very short way. And then when technical point of view, then Sanjeev sir and then all the faculty members, they collectively work very hard and make it is to success. And then also when comes to after commencement of this workshop, I am very much thankful, sir, for a very insightful all the lectures, right from Mahapatra sir and then Daniel Babu sir, and is given a wonderful lecture for the technology transfer and collaborative from the division, how we have to give the inputs to the technology. If anybody want to initiate in institute, it may be outside, whatever it may be. And then it's a very insightful and very important applications of production of radioisotopes as far and also and also the applications of radioisotopes in the human health. It is the twofold as it is highlighted by our today chief guest Dr. Tapas sir as far as the diagnosis purpose and also for therapeutic treatment purpose and also Ramanujan sir has given several lectures. One is radio analytical techniques and the other is the nuclear reactors and then also career opportunities for the DAE. Several lectures has been given by, and then Atunja sir and Sabisa sir has given regarding the basic interaction, how the radiation with the matter and then what is the ionization and non-ionization and then how the detectors are working and then our scientists like Chandrasekhar sir and then Sahilji is also given very much experimental demonstrations to our students. Our students are very much connected to their experimental demonstrations. They are very happy. So thank you very much, sir, for our wonderful lectures and our hands-on experiment inputs from your side. I am very much thankful to once again to the whole IANCAS for making it possible to come a long way to the BRC and conduct this wonderful and prestigious workshop. And thank you a lot. And already sir has given the official letter to our honorable principal sir. Sir has given the instrument as GM counter for the, especially for the both the academics and the research. Thank you very much, sir. That definitely we will make it into the practical. We will make it for the UG and PG practical, and also if it's possible we will do it for the research purpose. And also with the support of the principal sir, there are 2 more detectors that we have located from the department, and so that those also they have repaired. And those also we will use it for the both academics and research purpose. And thank you very much, sir. I think for this we have advantage a lot, both from the encouraging the students and imparting the knowledge, and also we got the equipment from the BRs and IANCAS. Thank you very much for your wonderful support right from the last 4 months to all these 5 days. Thanks a lot, sir. Thank you.
Seriously, that was really fast. Lot of points covered in just 5 minutes. Yeah, now I think it is time to thank our sponsors. GSL Hospitals, Coca-Cola Beverages, UBI, Indian Bank and Saujanya Hospitals, Dr. TV Narayan Rao garu, who financially supported this workshop. Now, I welcome the resource persons for their remarks on this workshop. First, I welcome Savisaj Patra, Dr. Savisaj Patra garu for his remarks.
Okay, I think the satisfaction in the faces of the participants says that they are extremely happy, and that is the precious gift that we are taking while returning home. So I wish you all the best for your future career. Okay, and I hope the classes didn't disturb you much. Okay, did you enjoy? Yes, all the class. So now you understand the basics as well as the working principle of detectors, right? Okay. So with this, I wish you all the best for future and maybe see you soon. Thank you.
Now I welcome Dr. Atunja sir for his remarks on this workshop, and I welcome him for addressing the participants.
Yes, hello everyone. Thank you all, first of all, for your warm hospitality. Then thank you for your kind attention throughout from the day one. You have been a very attentive students, very attentive participants, and like that, best wishes for your future endeavors. And in case of any doubts, we all have shared our email IDs. So if you have some doubt or you need some help from our side, so you are always welcome. Okay, thank you.
Now I welcome Sahir Mohammed sir for his remarks. Sir, please come and address the audience.
Respected dignitaries and my dear friends, good afternoon to all. So first of all, I want to give thanks to my head Tapas sir. 2 months back, he called me and said, you wanted to go Rajamandri. So I felt very happy because I am from Andhra. So I felt very happy, that too in government college. I studied in government college. So I felt very happy. And after that, I came here. And while coming from train, I heard about Rajamandri, but I didn't came. So నేను తెలుగులో మాట్లాడతాను ఎందుకంటే ఇంగ్లీష్ చాలా అయిపోయింది. ట్రైన్లో రాజమండ్రి వస్తూ ఉంటే జస్ట్ రాజమండ్రి టచ్ అయింది. ఎక్దమ్ ఫాగీ టైప్ అట్మాస్ఫియర్, ఎక్దమ్ ప్లెజెంట్, ఎంత మంచిగా అనిపించింది. గోదావరి చూసి చాలా హ్యాపీగా అనిపించింది. నెక్స్ట్ ఇక్కడికి వచ్చిన తర్వాత సార్ మన గౌరీనాయుడు సార్ వీళ్ళ అండ్ గ్రూప్ వీళ్ళు రిసీవ్ ఎలా చేసుకున్నారంటే, మేము పెళ్ళైన తర్వాత ఫస్ట్ టైం అత్తగారింటికి వెళ్ళినప్పుడు రియల్లీ మేము మా కలీగ్స్ చాలాసార్లు అనుకున్నాము ఇదేంటి మేము అత్తగారింటికి వచ్చామా అని. రియల్లీ ఫెల్ట్ వెరీ వెరీ హ్యాపీ. అండ్ స్పెషల్ థ్యాంక్స్ టు కోటయ్య గారు. ఎక్కడికి వెళ్ళినా సార్ ఏం కావాలి, నీళ్లు కావాలా, కాఫీ కావాలా, టీ కావాలా, సార్ 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 అసలు మమ్మల్ని అసలు నిలవనీయలేదు. థ్యాంక్ యూ కోటయ్య గారు. అండ్ ఇంకా ఇద్దరున్నారు, పేరు నాకు గుర్తు రావట్లేదు. అండ్ స్టూడెంట్స్, ఇప్పుడు ఇది మేము వర్క్షాప్, మీ ఫ్యాకల్టీ బాగా కష్టపడ్డారు ఈ వర్క్షాప్ కోసం. అండ్ మేము చాలా దూరం నుంచి వచ్చాము మీకోసం. సో ఇది టోటల్ ఎంటైర్ థింగ్ ఈజ్ ఫర్ యూ, ఫర్ స్టూడెంట్స్. ఓకే, నౌ ద బాల్ ఈజ్ ఇన్ యువర్ కోర్ట్. సో ఇప్పుడు మీరు చేయాల్సిందల్లా ఏంటి, మీరు చేయాల్సిందల్లా మంచిగా చదివి బేసిక్స్ ఇంప్రూవ్మెంట్ చేసి మీ ఈ కాలేజ్ నుంచి అట్లీస్ట్ మినిమం 10-15 స్టూడెంట్స్ బీఆర్సీలో సెలెక్ట్ అవ్వాలని మేము మనస్ఫూర్తిగా కోరుతున్నాము. ఓకే, థ్యాంక్ యూ ఫర్ గివింగ్ మీ దిస్ ఆపర్చునిటీ. థ్యాంక్ యూ సార్.
Thank you sir for your valuable remarks. So Godavari people are actually famous for their hospitality. We will never disappoint you. Now we will have a facilitation of our speakers and chief guest, and then followed by vote of thanks. So please stay about 10 to 15 minutes. Please stay back. అలా ఉన్నాయి. ఫెసిలిటేషన్ మీరు అనౌన్స్ చేస్తారా? Now I welcome Dr. Tapas Das Garu to accept our facilitation. Sir, please. All the faculty of the physics department, please come onto the dais. Next, I welcome Dr. P.S. Ramanjanelu Garu to accept our facilitation. Sir, please come. Thank you, sir, for accepting. Now I welcome Dr. Savisachi Patra Garu to accept our facilitation. Sir, please. Thank you, sir. Now I welcome Dr. Atanuja sir to come to the dais and accept it. Sir got lots of fans. Now I welcome Sahir Mahmood sir. Please accept our facilitation. Sir, please. Yeah. Power of experiments. Now I welcome our most beloved principal garu, Dr. Ramchandra R.K. Sir, please accept a little felicitation from Physics Department. Sir, please accept from the Department of Physics. Next. Madam. Thank you, sir. Thank you very much. Now I welcome Srimati Komal Lakshmi Garu, HOD Physics Department, to accept the facilitation. Students, all physics staff, please come on to dais, all physics staff. Thank you, ma'am. Now, I welcome the young chap, organizing secretary of this workshop, Dr. B. Gaurnaidu, to accept a felicitation. We wish him all the success for his future. Thank you, sir. Vote of thanks. Vote of.
All the faculty members that we bring pens to our all faculty members. Pens.
Okay. Yeah. Only faculty one. Sir. So all the physics department faculty members come on to the dais, and I also request all the people, the resource persons and speakers, to come on to dais. So they have a token of gratitude. They have small presentations for the faculty members. So not only East Godavari people, even the Bark people are famous for their hospitality. got already 2. Ma'am. No, I already got 2 actually. Yes. Thank you.
Sir. Sir, and Mr. Right. So I will visit in the month of April or May.
Yeah. Now we'll have vote of thanks by Dr. P.S. Ramandanelu garu. So just 1 minute.
Yeah. Okay. Don't worry, I will not take much time. Sir, 7:10. బయలుదేరాలి 2 minutes. రెడ్డి గారు కూడా వచ్చారు. ఓకే, ఐ జస్ట్ vote of thanks I have to say. Okay. Yeah, a very good afternoon to all of you. ఎనర్జీ తగ్గిపోయింది అప్పుడే. Okay, before giving my vote of thanks formally, first of all, my sincere apologies to all of you. If you are able to, suppose we are not able to meet your expectations, maybe. Okay. Okay. And before starting my vote of thanks, I just want to mention two more things. In the inauguration address, I expressed, you all should become brand ambassadors for DAE. Whether you all agree with me now or not. Okay. You have to popularize all our DIE technologies to your schools, wherever you go. That public acceptability should be increased for the DIE. Okay? And second thing, as principal sir already told about the school interaction students, the DIE already started Paramani Jyoti program. At present, we are going to the all Navodaya schools in various states. Now, the faculty members from the DIE who are going there, they used to call as a Paramanu Mitra. Actually, we have to spend schools for 2 days, and we have to interact with all the children, and we are explaining what this DE is doing. We call it as Paramanu Mitra. Now, the same role also here, instead of school children, you all are MSc students or faculty members. But our role is same. We are again Paramanu Mitras only. All our resource persons are, at any time you can access us, you can call us or give the mail. We are always ready to help you for any guidance or any problem in your life. Okay? And second thing, as Tapada sir already mentioned, if anyone is interested to become a member of IANCAS organization, you can go our website, I can fill the form and you can pay the something amount or 1,000 rupees, something like that. Then you can all become the life members of IANCAS. Then you will get all the informations wherever we are conducting the national workshops. Okay, now I will start my formal vote of thanks. First of all, I should thank IANCAS to choosing me as a convener for this workshop. And then I given the wonderful team, Sabi Chachi Patra, Atanuja, and Shahir Alam, Chandrasekhar. And I should say thanks to all my superiors, starting from Dr. P.K. Mohapatra, Dr. Daniel Babu Garu, and Tapas Dasar. They all are accepted our invitation to deliver invited lectures. And then I should say first thanks, sincere thanks to your government's arts college, and then respected principal sir, Ramachandra R.K. Garu, and our local coordinator, hero, Gauri Naidu Garu. See, generally, IANCAS will never accept any second time invitation within a 10 years. Komla Lakshmi Madam Garu, we should say thanks to her because she entered the team of faculty members of Department of Physics. They have done fantastic job starting from the inauguration to end. And then I maybe forget some of the names, but before that I should not forget Sudhakar Garu. Where is sir? Yeah. He organized entire workshop from starting from inauguration to up to the vote of thanks very coolly, very silently, and very efficiently. That we should appreciate from Sudhakar Garu. And one more thing, he also showed us the antique physics laboratory. It is there in the first floor. That's one of the fantastic thing I can see so far anywhere in India. All historical things is there. If possible, maybe in the summer holidays, I will bring my son. I am requesting you once again to show that same thing to us also. Okay? And then starting as Shahir Alam already mentioned, something like that, Attorinti vachinattigane undi maaku. Okay? And Reddy Garu, Venkateswara Garu, villandaru, Basha Garu. So maybe I forgot some of the names, sorry for that. But all your team members have done fantastic job. Thank you all once again. And then non-teaching staff, Kote Garu, and then Reddy Garu. They are treated as like that, like we are like kings. Then sometimes I feel very ashamed that the way they are treating us, whether we are worthful to that treatment or not. I really felt very bad about that. But really they are showed such a hospitality. We are impressed very well. Not only me, the entire team. And then I should say thank you to my resource persons also. The all Sabi Chachi Patra and Atanuja, Shahir Alam, Chandrasekhar, and all people have done fantastic job. And you should say thank you to one more person. Special thanks to whom? Shahir Alam is the quiz master. And he organized very fantastically that he prepared all the questions and asked all the people, encouraged you all the people. Thank you to Shahir. And before closing all, if I forgot any names, I am very sorry for that. And once again, I thank you all and wish you all the best for you. Thank you.
Somebody has to join.
Start. Other people will.
Okay, we'll close the workshop with our national anthem. All of you please stand up. Just join me. Janagana mana adinayaka jaya he Bharata bhagya vidata Punjabu Sindhu Maratha Dravida Utkala Vanga Vindhya Himachala Yamuna Ganga Utkala Jaladitaranga Tava Subhaname Jage Tava Subhashisha Mage Jahe Tava Jaya Gadha Janagana Mangaladayaka Jaya He Bharata Bhagya Vidhata Jaya He Jaya He Jaya He Jaya 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 He Jai Hind. Thank you.